This is from the layer.
No, that is it.
Oh, really? There's layer.
Yeah, I should 25 I would watch. There you go.
No, before we start with morning lecture, which actually will be the last lecture, on congratulations. Let me say one really important thing. This school would not be possible without contribution from Megan in addition, where she was
All right, so thank you for meeting for the lab day. Morning, everyone. And so wrap up the summer school with the lab lecture.
well, we're not wrapping up summer school with the last lecture.
Oh, yeah.
We are having your presentation after.
Mike.
No, sure. Oh, my, yes. Yes. And micro. Get with them. This one.
Okay, let's continue. So we'll continue what we were doing, and you more or less see, I hope, where we're heading. I will need one more example just to give you more simple presentation of what I want to do. And remember, the story was this, that both examples that we considered were like this. Yes, there are channels, superconducting channels, in which if we take Hubbard U, then effective interaction as a corresponding channels is zero. You don't get anything. We go to next order, we calculate irreducible vortex, and we find that attraction appears. And we know why attraction appears, because polarization bubble at large momentum transfer is larger than polarization bubble at small momentum transfer. And I already hinted that this likely means that the system wants to develop something else. And while developing something else, the system helps superconductivity to emerge. Let's now try to say this more explicitly and try to see how we can formulate this in more or less accurate way. For this, I will need one example where presentations are particularly straightforward and without extra excuse words that people will have to apply in other cases. And this is the case with Daniel considered in detail. This is the case of iron-based superconductors. The case of iron-based superconductors is interesting, unusual, because there are many orbitals, there is orbital physics involved, and there is also what is now called quantum geometry definitely playing a role there. But to me, I will present simplest story of iron-based superconductors in content of our story. So what I will do is this. Iron-based superconductors are often described either in one iron unit cell or two iron unit cell. The physical one is two iron unit cells. This is where our experiments are done. And this is the unit cell in which Daniel used in his lectures. And in this two iron unit cell, the story goes this way. There is a particular system which is iron selenium they're also strongly electron doped pnictides. Iron selenium is chunky genites. This system has only electron pockets. Other system has both hole and electron pockets. And so 2 electron pockets are like this. And Daniel discussed that in the presence of spin orbit, there is a splitting at this point, and you have 2 independent Fermi surfaces. But there are also hole pockets in the middle. 1 or 2 or sometimes even 3. Let me pull 2 here just to give you more straightforward example. And at this point, you may say, well, we go into boring business. We will not go into boring business. All I want to say is that what is hole, what is electron pockets? When people say electron pocket, it's conventional dispersion. Electron dispersion is like this. This is your Fermi surface. This is your occupied states, and pocket means that inside what I call Fermi, what I plot as a Fermi surface, states are occupied. Hole pocket is opposite. For this guy, dispersion is with the opposite sign of k square, if you like. And so then occupied states are here. These are empty states. This is why it's called hole pocket. Now, to make long story short, the stories that Daniel presented is the story about these 2 electron pockets. It's sometimes convenient, just for convenience of presentation, to go from 2 iron cell to 1 iron cell. You cannot do it when there is a spin orbit, because then you will have to include interaction between 2 different points in 1 iron Brillouin zone, I will put it this way. But for our purposes, it will be easy. All I want to say is that if you want to go into Brillouin zone in which there is 1 iron, not 2 iron in the unit cell, then you still get hole pockets here, but 2 electron pockets are this one and this one. And I do this just to mention that this immediately opens up 2 possibilities. One possibility is the one that Daniel described, which exists in the present, which is the only possibility when there are no hole pockets, is when there is repulsive interaction between these 2 pockets. Let's put it like this. And we played pretty much the same game as we played last time. Yes, there are 2 interactions, 1 interaction within this pocket, the same as one within this one. And there is also repulsive interaction at large momentum transfer, which takes 2 fermions from 1 pocket and brings to the other pocket. Just like we did with patches. Instead of patches, we now have pockets. That's the only difference. And then, not surprised, if you forget about this one, let's forget about this for a second. This is a monolayer iron selenium. Then the only option that you have is gap delta here and minus delta here, right? If, of course, if interaction repulsion between pockets somehow gets larger than repulsion within pocket. It's exactly the same story as in cuprates when we had patches. We basically said consider these 2 patches, right? And when interaction repulsion between patches U2 gets larger than in repulsion within patch U1, you get superconductivity with delta minus delta. Exactly the same story goes here. And of course, it's D wave. Why is D wave? Not because there is a gap on any of the pockets. It's because when you rotate by 45 degrees, when you rotate by 90 degrees, you change the sign of the gap. So in terms of rotation, then this is like cosine to theta. You rotate by 90 degrees, your gap changes sign, right? So this is D wave gap. And once you merge these 2 guys into 1 point, when you go into 2 iron zone and then introduce spin orbit and actually split this points into 1 large Fermi surface and internal one, which is smaller one, then gap on each of these Fermi surfaces will be perfect D wave, and it will have nodes. The story that I will be talking about is a different story. And it's one of competitive pairing states that people discuss in iron-based materials. In iron pnictides, with one exception, they all have both hole and electron pockets. Then the story goes like this. Then yes, you have two electron pockets. Let's go back to physical two iron zone, and we have hole pockets here. And then the story that seems to be very much in line with experiments is let's consider interaction between these pockets and these ones. I will simplify problem. I will just, instead of two, I will take only one here. Instead of two here, I'll take only one. And then you see that we again, you'll be bored with this. We again go back to the same story as before. There is one pocket in the middle, one pocket in the corner. We can again introduce two interactions. One, let's continue calling it U1, will be within pocket, meaning all fermions are close to one pocket. And there is another interaction, which I label U2, which will be between pockets, right? No difference with this one. The states that you will get, if we are lucky and we get attraction, in every case that we consider, we need to check, do we get attraction? We go to second order in the interaction and check whether this U2 gets larger than U1, right? But the states that, assuming that we get it, the states that we get will be the same delta minus delta state. It always goes like this, right? Only now what we will get is delta here and minus delta here. And this is what is called S plus minus. Why S? Because I can make a circle in this pocket. I check symmetry of the gap. I rotate, right? And when I rotate along the Fermi surface, nothing happens. It's a constant gap. But it's not S wave. This gap is plus, this one is minus. Well, it's called, sometimes called extended S wave, but better notations that everyone uses is S plus minus. And I hope I gave you a hint that this physics and this physics and this physics, it's all the same physics. And the physics that we had before with the hexagonal situation when we have 1/2 points, it's also the same physics, right? And what you have in many other systems, including twisted tungsten diselenide, it's also the same physics. But the reason I wanted to focus on this is that here some things become more clear. Namely, remember the story that was our subject last lecture, second part of last lecture. We said that in order to get this, or this, or this, we consider two quantities. We consider particle Hall bubble at momentum q equal to 0 and particle Hall bubble at momentum q equal to capital Q, where capital Q is distance between players. Actually, in all these cases, distance is pi pi, right? For a hexagonal system, distance was not pi pi, but for this square it's always pi pi, right? And the story in all these cases was that particle Hall at q equal to capital Q is larger than particle Hall bubble at q equal to 0. Right? But at the same time, our story was always like this. Yes, there is one constant, another constant, one constant is larger than the other constant, but we still in the back of our head had in mind that we are talking about irreducible interaction in a particle-particle channel. And why we are doing this, why we introduce this quantity, because we know that in a particle-particle channel there is a Cooper logarithm, right? So the stories that we had before was always like this. Yes, there are some constant renormalization that transforms interaction UI into UI tilde, and this is irreducible one, but it's transferring one constant into the other, right? I mean that particle-particle channel was always separate from everything else because of Cooper logarithms, and then we know how to sum up Cooper logarithms, right? We know that once we get attractive interaction, we're guaranteed to have instability. Let me challenge this. In fact, I can challenge it for all cases, but as I said, calculations are most straightforward and most simple for this case. So let me try to calculate these quantities. And I try to compare this with polarization bubble and a particle-particle chain. Since I'm going to compare, let me go back for a second and calculate with you what is we normally call particle-particle polarization. When there was, let's put it, there is a momentum L and minus L, there is a frequency omega and minus omega. Let's remind ourselves how we get Cooper logarithms. We need to do, let's do it at 0 temperature just for simplicity. So omega will be Matsubara frequency, again for simplicity. And then each line is a green function, right? So my green function is 1 over I omega m minus epsilon L. And epsilon L includes chemical potential. K squared over 2m minus chemical potential for simplicity. So when I take a product of these two green functions, when I write down polarization as particle-particle, no, this of course particle-particle, two lines in the same direction, the momenta L and minus L, right? Then you all know what to do. We get integral over d omega, let's call it m. M means Matsubara. 0 temperature, remember, first rule of diagrammatic technique. At finite temperature, you have to sum over Matsubara frequencies. At 0 temperature, just integrate. This is why nowadays, if you don't need specifically to study transport properties, all calculations are done in Matsubara frequencies. It's just easier. So, and we need to integrate over whatever dimension of momentum L is of what? 1 over I omega m minus epsilon L and minus I omega m minus, I should put epsilon minus L. But epsilon minus L is the same as epsilon L. We have inversion symmetry. Minus epsilon L. And this always happens for conventional dispersions. When I change momentum to minus momentum, dispersion remains the same. And obviously, this is integral over d omega m. I translate integration over d-dimensional dl into density of states at the Fermi level times integral d epsilon L. And what I have in denominator will be omega m square plus epsilon L square. You may say, well, what I'm doing at the lecture number 4, I'm supposed to do it in lecture number 1, right? But anyway, we know this. This integral is logarithmically singular, right? You don't even need to integrate over omega, you can do summation. But if the integral is obvious, so 1, 2 variables, square of one plus square of the other. This gives you log. This is what's called Cooper log. This gives you an f times logarithm. Logarithm you need to cut, and we normally cut by external frequency. You can cut by temperature, and this log of some upper limit divided by same mod omega. And we say, why I'm doing this? I'm doing this because now I want to do different things. I want to look into this quantity. Particle hole at this quantity. Particle hole at momentum q equal to capital Q. And let's play the game about best case scenario. Let's assume that we're at charge neutrality and the size of this pocket is equal to the size of this pocket. So just completely equivalent hole and electron pockets, so that total number of, if you like, electrons is equal to total number of holes. Very good. Then what I have here, I need to calculate particle hole at Q, and I write it again as, now I have two green functions. Errors are different directions, this particle hole, right? If this frequency is omega m, this is frequency also omega m, right? Now this dispersion will be epsilon L. And what I have here for another one, remember one branch, this one is branch going up, this is the branch which goes down. And it's just one is mirror image of the other, right? So then we have interesting story, minus epsilon L here. Not because dispersion changes, I have to write down, yes, epsilon L, right? It's just like instead of frequency, I change sign of dispersion. And the reasoning here is quite straightforward. One dispersion is hole-like, another electron-like. They're just mirror images of each other. So what we have here, we get particle hole at momentum q equal to integral d omega. Let me write down immediately nf integral d epsilon L. What I have in denominator, I omega m minus epsilon L is this green function. I omega m plus epsilon L. It's another green function, right? Very simple. But as a result, with overall minus sign, it will be nf times integral d omega m d epsilon L omega m square plus epsilon L square. And here you're saying, interesting, it's the same logarithm. Yeah.
Is it for 0Q or is it for finite?
No, this is capital Q. This is why I put epsilon L. It's a particle hole made out of these two guys. This is why one dispersion is up, another is down. If I were to do this at Q equal to 0, then I get I omega minus epsilon L times I omega minus epsilon L. And then I will get no logarithm. That integral will vanish. Both poles are in the same half plane, right? But here you clearly see what's going on. You can integrate over frequency, and you immediately see that the poles of these two expressions are in different half planes. But you see it also here. And this gives you minus NF times the same log omega naught divided by mod omega. And now we have interesting situation. We have two channels, and they're both logarithmical. And this is where randomization group studies come to help us. So what it means? It means that our story that we calculate irreducible vortex in a particle-particle channel and then sum up in a particle-particles doesn't work anymore. Because of completely equivalent calculations, we can say, well, why don't I calculate irreducible vortex in a particle hole channel with this momentum? And then sum up the corresponding graphs. I again will get some of the logarithms. So what should I do in this situation? And first of all, question, is it clear? Because I'm going to erase some part from the whiteboard. Any questions? Moving on. Great. So in this situation, in fact, what we have to do is to ask ourselves, generally, if I ask all of you, what should I do? Well, somebody will tell me I have to sum everything in both channels, right? I have logarithmical series in a particle hole channel. I have logarithmical series in a particle-particle channel. So I have no choice but to sum everything, right? Which looks that it's quite impressive task to do, right? And it is impressive task to do. And we'll do it. But before we do this, let's see what are the players. The players are, first of all, there is definitely interactions that we had before. This and I use different colors. Let me still try to use different colors. So let's do it. red and blue. So this would be red, this is blue. So there is one interaction that we had before. It was like this. And it was the same as blue, right? Oops. Which one is blue? Probably this one, right? Confuse this two. Let's now keep notations. This is what we call U1, right? There was another guy that we discussed. It was like this. 2 from 1 go into the other, right? And other way around. We can also get this and then this. And we call this object U2. This is an object we so much like when we talk about pairing channel, because these are objects that get renormalized using Cooper logarithms, right? But we also, if we play the game with red lines and blue lines, we also have two other possibilities. One is this. I go from red to blue and simultaneously from blue to red. That's what basically is exchange interaction. I go from one to the other. Can I do this? Yes, I can. Remember, the distance between these two guys is phi pi. So you can easily verify that momentum conservation is satisfied. But it's generally satisfied anyway, because the sum of these two guys is close to pi pi, and the sum of these two guys, the momentum of these two guys is close to pi pi, right? We call this interaction normally U3. There is one more choice. And one more choice is this. Line, interaction, and another one. It's called density-density interaction between pockets. Inter-pocket density-density interaction. It's density in one pocket and density in the other pocket. Momentum transfer here is small, but total momentum of these two particles is close to pi pi, right? And this calls this interaction U4. And you know what's good? You cannot write anything else in terms of blue and green, blue and red. Just no way you can do it. Now, why we are doing this? Because we know that if you can trust me in one word here, that, yeah.
So these diagrams, so initially we were doing the previous cases, we only had U1 and U2 because there were no whole pockets on the Fermi surface. These terms become relevant because of the existence of a whole pocket on the Fermi surface.
This diagram, these two other interactions become relevant, and I call them with names, U3 and U4, because of the next phrase I'm going to say. That if you write diagrams for the renormalization of this, U1, U2, let's forget at this stage with the word irreducible. Let's just do brute force perturbation theory. We renormalize this interaction. We know that these two guys get renormalized in a Cooper channel, right? So there is a Cooper log. Let me call log by L, just not to write it every time. So I call this L. So this renormalization contains L. What about these two guys? And it turns out that their renormalization also contains L, but it's different L. It's L from particle Hall channel. But L is L, no matter where it comes from. So their renormalization also contains L. And then my task is this. I don't want any renormalizations that do not contain L. This will be something small. Remember, L is a large parameter. I can make L as large as I want by making frequency smaller and smaller, or making temperature smaller and smaller. Now, this scale could be either frequency or temperature. So what I want to do, I want to keep all renormalization which contains L. And I want to neglect all renormalizations that don't contain L. In particular, here I don't lose anything because this guy contains L, this does not, right? So I just simply strike it out. It's my best case scenario, right? Good interaction get renormalized by a logarithm. Bad interaction doesn't get renormalized by anything, because remember what I say, good and bad. This was a normalization of U2, and this was a normalization of U1, right? And U1 is a bad guy for me. I need U2 to get larger. So I keep all this, but in the process, I also have to keep in mind that interactions that provide this renormalization, they also renormalize logarithmically. So everything flows. By flows, I mean that everything changes when I change external frequency. In order to analyze now more serious, more sophisticated flow, more complex flow, when not only these two interactions renormalize, but also these two, I need to sum up all possible logarithmical terms, which seems to be, as I said, quite impressive task of writing all these diagrams one by one and then realizing where these logarithms come from, etc., etc. And to simplify story, but the story can be simplified enormously. And this is where RG approach comes in. So RG, there are several approaches which are called RG. There is RG when you progressively integrate out high energies, and come to lower energies, and then you don't care what you get, you just do approximate calculations. I can say a number of words about this, but let me avoid this. I will use RG as intelligent way to sum logarithms, because this is where RG is well justified, and this is where it actually has been applied, first of all. And I will explain what I mean. Let's go back. And this will be the last exercise in going back. So I again go back to what was in lecture 1 by me, by Nikolai, and also by Danny. BCS theory of superconductivity. Let's use this. I hope it will not take more than 5 minutes. Go back to BCS. What is BCS? Remember, we start with the interaction. You forget about all spin indices. We know that it's, we start with constant interaction. So we know that it's spin singlet. So we start with interaction U, and then sum up ladder diagrams, right? So we need to get what I would call fully dressed interaction. It's not irreducible. This is fully dressed. Irreducible was with horizontal line. This is full. So I get, and if I do only Cooper channels, that I start with interaction U, and then I start writing this, and then I start writing that, etc., etc., right? You already saw this number of times to get Borchardt. This is just standard summation of Cooper logarithm. Let's look at the result of this summation, something that we also discussed number of times. U bar, dressed U. We don't include any renormalization from particle Hall channel because we only want to focus on logarithms. And this is not this story. This is just simple BCS story. One band, just one interaction, and let's assume that it's even attractive. So here is what we know. You know the solution. U1 minus U, let's do it in 3 dimensions, MPF over 2 pi square times logarithm. Logarithm I already wrote, so it's book capital L here. Very good. We know this. This is BCS. I'm not doing anything else, right? In order to get this formula, we need to sum up this infinite ladder series of graphs, right? Now let me look at the answer. And I will just try to simplify answer a little bit. I will introduce dimensionless coupling. Dimensionless coupling, I call it lambda. It will be equal to, remember, I did this, let's write down plus U, because this is what we need to do. And then we have attractive U negative, so it will be 1 minus mod U, right? Mod here. Right? It's just accuracy, nothing else. So dimensionless coupling lambda, which will be MPF over 2 pi square times mod U. By definition, this coupling is positive, right? So then what we get if I multiply both sides of this equation by MPF square over 2 pi square, which is nothing but density of states, which means that I can do calculations in any dimensions. This was a specific example of 3 dimensions, but I can do it in 2 dimensions, in 2.5, whatever. So the same equations will be like this. Lambda bar is equal to lambda 1 minus lambda times log. Right? Agree? It's trivial. Now let me tell you that this is the solution of differential equation. And differential equations like this. I need to say one phrase before I go to differential equation. Let's view this as, we know, let's start the phrase again. We know how we normally view this. We discuss this. Yes, there is denominator, and at some value of the logarithm, read it at some particular temperature or at some external frequency that you put in, you will get a pole, and pole would mean that there is instability, right? If lambda defined like this is positive, right? We can view the same result. I'm not getting different result. I'm just trying to get different meaning of the same result. I can view lambda bar as a running coupling at value of the logarithm. And remember, L is logarithm omega naught divided by omega. So it's just like, say, I view this as a running coupling at some frequency omega. It's just more convenient to me to talk in terms of logarithm of quantities than the quantity itself, because everything depends on the logarithm. So I can view this as a running coupling. Running means changing coupling as a function of the logarithm. And then at particular value of the logarithm, this running coupling will go to infinity. This will be my instability. I didn't say you anything besides BCS formula. But viewed like this, I can write down the same equation as lambda bar of L is equal to lambda, which now is my bare coupling, the one I start with. Remember, this is my U, my starting interaction, divided by 1 minus lambda times logarithm. Very simple formula, right? And again, just plot it. When lambda is positive, if I start with positive lambda, then my lambda bar, let's put it like this, this is my logarithm, this is my lambda bar. My lambda is my bare value, whatever I put in, it's a number, right? So this function, obviously, at some value of the logarithm, which is 1 over lambda, will just diverge. Divergence means instability, right? So I now rephrase instability. It's just like susceptibility, but viewed differently. Running susceptibility is a function of running variable. Now, the main part here. The main part here is that we don't need this expression anymore, right? We need everything in terms of lambda. And let's put it this way. That this equation, which we obtained by summing up Cooper logarithms, can be also written as solution of differential equation. What is this differential equation? D lambda bar over dl is equal to lambda bar squared. Solve this. You know how to solve differential equation, right? D lambda bar over, and yeah, and sorry. And with any differential equation of first kind, of first order, I will need one boundary condition. My boundary condition is when frequency equal to omega naught. This is where I start. This is my high energy physics, right? So this condition is lambda bar of 0 is equal to bare lambda. This is where there's no randomizations whatsoever, right? So solve this equation. What is this? D lambda bar over lambda bar square is equal to DL. differential of 1 over lambda bar is equal to minus differential of L, right? Right? So 1 over lambda bar, 1 over lambda bar is equal to L minus L, sorry. And when L is equal to 0, lambda bar is lambda. So it's equal to plus 1 over lambda, right? That's our 5-second solution of differential equation, right? Very good. You see immediately lambda bar is equal to lambda 1 minus lambda L. The same equation, the same solution. Which means that we can replace summing up series of graphs with just one differential equation. What it means in terms of how we do calculation. The way how obtain this expression. We basically say this. That yes, I still have to remember about ladder series. But what I do is this. I know that there is an infinite number of terms here. I take some of these terms. I take this one. And choose one cross section. Say, let's do it 4, it will be easier. I choose this cross section. There is a frequency omega prime in this cross section. There is some external frequency, which I call omega. Right? So what I do, I'm saying after I chosen this cross section, what are my infinite series of graphs? It means that I can sum on both sides of this cross section, writing 1 interaction, 2 interactions, 3 interactions, 4 interactions, etc. So you may say, well, you do the same. You just rewrite your ladder series in different way, which is true. I don't do anything else. It's the same equation, so the same solution, etc. But this way, situation looks like this. When I sum all the series, that means that I sum infinite series on both sides. What I get is the coupling lambda bar as a function of omega prime. Why I'm saying omega prime? Because remember what is logarithm. Logarithm is an interesting function. If I integrate from omega to omega naught dx over x, where does this integral come from? It's a funny function. It comes from x, on one hand, much smaller than omega naught, on the other hand, much larger than omega, right? What I mean specifically, that if I integrate dx over x from omega to 3 omega, what's the result? Well, you know the result, log 3, right? Agree? Where is omega? Gone, right? So as long as I keep upper limit, 10 omega, 20 omega, it will be number, which means that integral comes from internal frequencies much larger than this omega. I use it here. I'm saying that this vertex, when I get log omega, which means that all internal frequencies are much larger than omega. This is how I get logarithm. And I use it here. I assume omega prime will be much larger than omega, but in logarithmical sense. Meaning that when I integrate, I have to integrate over window. I take these guys, which generally depend on running frequency, omega prime, and external omega. The story is that you can check it immediately in calculations. It's always a function that depends on the larger parameter, not on the smaller. So this becomes a function of running frequency omega prime. So now what I have, look, when I want to do, this is a full series. I sum up here, infinite series. So what's the result? The result will be lambda bar will be equal to integral from omega naught, from omega to omega naught, d omega prime. We know that there is, when I sum up over these two green functions, I get logarithm, right? So I get over omega prime, and then lambda bar square of omega prime. Right? Agree? Which is a function of, in fact, a function of logarithm of omega prime. So I can rewrite this result. It will be integral from 0 to L d omega prime over, integral dl. L means logarithm. This is differential of logarithm. And then lambda bar square L prime, L prime. Again, I claim that this is a full series because this is full summation. Only now, previously I said, let's sum them one by one. Now I choose one cross section and sum on both sides of this cross section. With logarithmical accuracy, I can do this. It's equivalent procedure. I can either do ladder summation or I can choose one cross section and sum on both sides. Now, what we get? Let's see. This lambda bar, which you want to calculate as a function of lambda, contains the same lambda bar under the integral, right? So technically, this is integral equation, right? But there is one beauty thing. If I take derivative of upper limit, if I take d lambda bar over dl, and you hope you understand, when I went from this to this, I just introduced new variable, d omega prime over omega prime, it's a logarithm, and then basically logarithm will be between lower limit, which is 0, and upper limit, which is L. So remember what is to take integral over upper limit? What is this? It's a function at the upper limit. It's lambda bar square. Same differential equation. We solve it, we get a result. What it means for our purposes, it means that we don't need to sum up series. We don't need to write down this infinite series of diagrams. We write down second order diagrams, only second order. This we can do, right? And then replace all lines in this second order diagrams by the running variables. And then differentiate upper limit. This is what we have to do. And then we write down differential equation. And this is doable procedure. I mean, what we have to now go back to what was on this part of the blackboard. We had 4 interactions. Let's translate all of them into dimensionless. I multiplied all of them by density of states. Previously I had U1, U2, U3, U4. Now it's lambda 1, lambda 2, lambda 3, lambda 4. Again, lambda is nothing but U times density of states. Very good. So this is now lambda 1, lambda 2, lambda 3, lambda 4. The only difference here is that, it's not a big deal, the difference, is that here I said from the very beginning, let's assume that the interaction is attractive. And I define coupling constant with modulus of u, which means with minus u. Let me now define coupling constant without minus. If I define coupling constant without minuses, there should be 1 plus lambda here, right? And then negative lambda will give you the result. What it means from the point of view of differential equations. How to get solution which will have 1 plus here instead of 1 minus. Very simple. There should be overall minus here. dl bar over d capital L, d lambda bar over d capital L should be minus lambda bar square. And then you'll get solution. So now, here is what we have to do. We don't have time to write down all graphs. And if I write them, you will be sleeping. But you know what to do. We take all of these guys, we write down, we forget about what is irreducible. We don't care. Pairing channel is no better than particle Hall channel. So we write all second order analyzations, like, for example, we can do this, right? But we also can do, for example, let's see, we go right. we go from red to blue. And we do it like this. We do bubble like that. And we again go from red to blue. This is normalization of lambda 2, right? Two incoming are from red, two outgoing are from blue. This is the guy that was there. It's U2. It's a good guy, right? Again, lambda is nothing but U times density of states. And now see what it has. It has this wonderful stuff. What is this? Particle hole bubble made out of red and blue. This is now another logarithm, right? And so we look only at the diagrams that contain L, logarithm, either in a particle-particle or in a particle hole channel. We don't include diagrams that don't contain L simply because we don't know how to deal with these diagrams. But remember, we still have weak coupling. Our couplings are supposed to be small. Very good. So we write down second order diagram for the normalization of this guy. And then in these diagrams, we replace all interactions, either this one, this one, this one, this one, by the running couplings. And then write down differentiate over upper limit. And then we get set of coupled differential equations. And believe me, it's not difficult to do this. Meaning that we know how to write second order diagrams, right? And number can be large, fine. To select which one are logs is very simple. Either this, right? Or this. Or this. These are three sources for log. For example, if we have some diagram which contains bubble like this, we don't include it. It doesn't contain log, right? So once we did it, second order diagrams, replace all coupling by running one, we get guaranteed that we sum up all logarithmical terms. And this is what is called parquet renormalization group. Parquet, you know by the word parquet. Parquet, it's, make idea, why it's called parquet.
Because it looks like the floor.
Sorry?
It looks like the floor.
Yeah, because look at this. This looks like horizontal line, right? This looks like vertical line. If I add one, I go vertically. Bubble, 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 bubble. So this is how I make parquet, right? I go this way, I go that way, I go this way, I go that way. Seriously, this is why I call parquet. It's just like you do flooring. Yeah, and you can check. In fact, people check this. That yes, if you don't trust all this, if you want to go back to boring summation of logarithms, go to next order. Just check that what you get by summing up accurately, boring, summing up logarithmical terms will be exactly the same as solution of differential equation. What is nice thing here, that I have 4 parameters here, right? In the 5 orbital model for iron superconductors, the number of couplings is 48. So you can write 48 coupled differential equation. But doable, because all we have to do is to write down, yes, it takes about half a day to write down the second order diagrams for this of 48 couplings. Remember, you only need to choose the ones that contain log, and then write down differential equations. Yes, it will take 2 pieces of paper to write down these equations, but you can be, it's done, right? And by the way, if you then put it in Mathematica, Mathematica will give you a solution right away. Mathematica don't care about there are 48 differential equations. As long as they're simple differential equations, you get solution. Okay, so what we have here? Let's not do derivation on a whiteboard. I hope that it's clear what to do. So we have 4 differential equations, 4 variables, and the equations are, I think it should be here. Just let's see what I get. Right, here are the equations. Lambda 1 dot, by dot I mean lambda I dot is d lambda I over dl. Dot just derivative, nothing else. So lambda 1 dot is equal to minus lambda 1 square minus lambda 2 squared. Lambda 2 dot is equal to minus 2 lambda 1 lambda 2 minus 2 lambda 1 lambda 3 plus 4 lambda 2 lambda 4, and we also get lambda 2. Right. Very good. Lambda 3 dot is equal to 2 lambda 3, lambda 4 minus lambda 3. And there is also lambda 4 dot is equal to lambda 4 square plus lambda 2 squared. Very good. What it means? First of all, we notice interesting stuff. That this guy is pretty good. By the way, the equation is written such that initial lambda are all positive means repulsion. I hope I don't confuse you. In the BCS case, I use modulus of u for lambda. So positive lambda here means repulsion. And you see that this guy only goes up, no matter what, right? Let me go back and check with you one thing that's always good to check. What if we forget about what I tell you and only consider Cooper channel? If I only consider Cooper channel and forget about particle Hall normalization, then equations simplify in this way. I don't need to worry about what is lambda 3 and lambda 4. They are not vertices in a particle-particle channel. They don't contribute to superconductivity per se, right? So here's what I get. Then lambda 1 dot is equal to minus lambda 1 square minus lambda 2 square. Lambda 2 dot is equal to minus 2 lambda 1 lambda 2. Right? Very simple. Meaning lambda 1 plus lambda 2 dot is equal to minus lambda 1 plus lambda 2 squared. Right? Meaning that this quantity goes down all the time, no divergence guaranteed, right? Derivative is always negative, right? So this solution of this equation will be lambda 1 plus lambda 2 will be equal to, I have to be careful, bar. Of course, everything is bar, and nobody told me about this. Of course, it's all bar, right? It's not a bare value, it's a running value. So all of them are bar, running. Guys, if you see this, let me know. So bar, 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 bar. Then I have to be careful. Lambda 1 dot plus lambda bar, 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 bar. Then lambda 1 plus lambda 2 bar will be now bare lambda 1 plus lambda 2 divided by 1 plus lambda 1 plus lambda 2 times logarithm. Does it resemble you something? This is what we get for S-wave channel, right? Same result. And another one, right? Out of these two equations, we can get two. This will be first. And the second will be lambda 1 bar minus lambda 2 bar dot will be equal to minus lambda 1 minus lambda 2 bar. Right? Agree? And here the result will depend on the bare value. You will get lambda 1 minus lambda 2 will be equal to lambda 1 minus lambda 2 divided by 1 plus lambda 1 minus lambda 2 times log. This is the solution of this equation. You can check. This is the solution of this equation. And then you immediately see that when lambda 2 is larger than lambda 1, you get instability. Right? So we get exactly the same as we had before. In this respect, differential equation in Cooper channel, differential equation and summing up Cooper logarithm are a completely identical procedure. It's just another way to think about this. what this differential equation helps is to write down what happens when we have more than one logarithmic channel. Then, of course, I don't think that you will be able to tell me immediately what's going on, how to write down this equation. Very good. So we found, right, that if we forget about everything else, we go back to what we had before. Yes.
So like your differential equation is inspired by this ladder series, which you're almost going to erase soon, right? And later you said, okay, I'm gonna replace these wavy lines, these U by running couplings.
Yes.
But now you don't care about the irreducibility of these running couplings.
Sorry?
You don't care about the irreducibility of.
No, I don't care.
But
I don't care.
you running through a scenario when you double count the diagrams?
No,
You
no,
don't-
I don't count anything. I don't double count anything. It's ladder series here.
Yeah, but like inside the running coupling, if you also put ladder, then you have a ladder of a ladder.
Right. Which means that I have to forget about the word irreducible. I don't know what is irreducible. Irreducible to what? I mean that I still can, well, I can introduce irreducible interaction on a particle-particle channel, but it's meaningless because this irreducible contains the same logarithm that you had in the Cooper channel. So it's meaningless. This is what I said. Forget about the word irreducible. Sum up all graphs. Just everything. And when you do this, this is what you get. Is it more or less clear? Okay. For whom it's completely unclear. This is good. Questions at this stage? Let's move on. So let's look at the result, right?
Just you confuse further.
Yes.
Formally lambda 1 equals lambda 2 because we start from the Hubbard, right?
Yes.
Formally.
Yes. Formally, yes.
So
Let's
we have
do
nothing
it.
anywhere.
Let's do it. If I have,
No, I'm just simply saying if you forget lambda 3 and lambda 4, the answer is there is nothing.
absolutely, but now we don't forget. So sorry.
And what about spin? Does it introduce 1/2 or something to get rid of the cancellation?
No, this is all included. There's spin full fermion. So every time when you write bubble, you have to put a factor of 2 because of internal spins. This story.
So it's a sheer difference without 1/2 in front of lambda 2, right?
Sure, equations are correct.
All right.
Equations are correct, but I erased equations, which I don't have to do. Okay, so point is this: you do conventional perturbation theory. All spin summation is there, and spin summation in diagrammatic theory is nothing but every time I have a bubble, right, put a factor of 2, actually -2 with respect to bubble, minus because of rule of diagrammatic technique, 2 because you sum up over internal spins. So what do you have? Let's write down again. Lambda 1 bar dot is equal to minus lambda 1 bar square, plus lambda 2 bar squared. Lambda 2 bar dot is equal to minus 2 lambda 1 minus 2 lambda 3, but now plus 4 lambda 2 lambda 4, lambda 3, it's equal to 2 lambda 3, lambda 4 minus lambda 3, and lambda 4 dot bar dot is equal to lambda 4 bar square plus lambda 2 bar square. Okay, good. These are the equations.
This is the first one.
Yeah, minus. Thank you. Minus. Right. Okay, now it will be great, of course, to spend the remaining whatever time I have to solving this differential equation. But let's look at physics. Physics is this. Just knowing what the result is and what the physics will be. Let me simplify this equation in one aspect. I can go here. Just to understand what's going on. So remember, lambda 2 is a good guy, right? Lambda 1 is a bad guy for superconductivity. You saw it here, right? In order to get something, this guy should be larger than this one, right? But don't overshoot this expression. This is just Cooper channel, only Cooper channel. So we probably better even erase this, because now we solve for all equations. And here's one simplification I want to do just to show you what the results are, or what the tendency is. It turns out that this interaction doesn't play much role. And of course, you can check it only when you solve the full equations, etc. But just for our understanding what's going on, let me for a second set lambda 3 equal to 0. And you know, bar, of course, bar. It works. If this guy is 0, then derivative is also 0. So this guy expressed in terms of itself, right? And it also means that lambda 3 will always be proportional to the bare value. So it's enough to have bare value of lambda 3 equal to 0, and then it will never be generated. It's a property of equation x dot is equal to x times something. Solution is always proportional to bare value of x. Then let's see. This guy is a bad guy, and you see bad guy only goes down, right? So let's write the bad guy, lambda 1 bar, as a function of L, no matter what's going on. This guy goes down, right? Very good. It goes down. Now there's a good guy. And with the good guy, what we have? We have this term. This what we had before. Forces it to go down. But then we have this guy term. We had push with opposite sign, right? From war, from the guy which by itself can only go up. So now run the system. Put boundary condition, whatever we want, and let the system run. When the system will run, this guy immediately will start running up, right? When it becomes larger, this guy becomes larger, right? And when this guy becomes larger, then it will change sign of the derivative of lambda 2. And the derivative, in fact, will be positive rather than negative. And in fact, check one thing right away, that if I want to go to second order without RG, just simple what we did before, Kohn-Latinger, second order normalization. What is second order normalization? It's solution of this equation to first order in L. So you solve this equation in iterations. You assume that bare values are lambda, and then solve differential equation as correction to bare values, to first order in variable L. You know how to solve differential equation in expansion, right? Basically, it means that you put here, when you write differential equation, you put here bare values, and you immediately see Kohn-Latinger. It immediately shows up. It's all there as a first order term, but we now went all the way. We summed up infinite series in particle hole and particle channel simultaneously. So suppose I start, Nikolai said, what if lambda 1, bare lambda 1 is equal to bare lambda 2? Well, we know Kohn-Latinger will give you attraction. And what if not? What if I start with a situation which I put here, when I try to be more realistic, right? Remember, lambda 1 is interaction at small momentum transfer, lambda 2 is the interaction at large momentum transfer. So naively, I would say that lambda 1 should be larger than lambda 2. If I look here, it means nothing, right? Very good. Let me put lambda, this was lambda 1, right? Bare value. Let me put lambda 2 here as a bare value. The question is, I run these equations, what happens? And I already tell you what happens. This term forces lambda 2 to go down, but this guy forces it to go up. And then you ask who wins. And it turns out that this push wins. Maybe not initially, but at the end of the day, push wins. So what happens is that even if this guy initially goes down, it will go up. And what it means? it means wonderful thing, that the system self-generates attraction. Moreover, it self-generates a scale below which it has attraction, this scale, L star. It's not a phase transition, nothing. It's just a scale. What I say below which, larger L means smaller energies, right? L is logarithm omega naught over omega, smaller omega, larger L, right? So almost fantastic thing. The system with the initially repulsive interaction, look at this. Interaction was repulsive, right? In the process of this RG flow, generate attraction. And do we violate weak coupling story here? No, because remember, all our bare couplings are small. So all our lambda bare values of lambda I are smaller than 1. And you see where the crossing is. This guy goes down, this guy goes up, and they cross. So at the crossing point, couplings are still smaller than 1. Right? Because this guy is smaller than 1 and we only went down. So we are still in weak coupling, which means that this unique case, when we do weak coupling analysis and go to infinite order. And you may say, well, we know example, BCS. BCS is a situation when we can take weak coupling and sum up logarithms and go to infinite order. Here we do the same, only 2 channels. And now we can ask what it means physically. It means physically that there's some other guy, and some other guy is this one, that does interesting things. It pushes good part of the pairing interaction up. It doesn't do anything to a bad guy. Bad guy will die by itself, right? But it pushes good guy up. And this is definitely a result of lambda 4, right? Very good. Now I can ask a question, and what lambda 4 does by itself? This interaction, which keeps going up, right, becomes larger and larger and larger. What it gives. And for this, we need to check what it gives. And I argue that it will give you magnitude. How you can see it? You need to do exactly the same as we did for superconductivity. Namely, what we did for superconductivity. We said, well, there was a channel in which we have logarithmical singularity. Then we more or less understand what, or we guess what it means. And we said, well, it means that susceptibility with respect to infinitesimally particle-particle vortex becomes infinite, right? This guy is not in a particle-particle channel. And the reason why it goes up, you don't see it, of course, but you can check in the formulas. The reason why it goes up is because it contains logarithm from particle whole bubble, not from particle-particle. And then let's do it here, because this is a part where we can do calculation. So this is, we can ask what happens if I introduce now infinitesimally vortex with 2 fermion, one with whole pocket, another with electron pocket. Remember, this interaction was density of hole, density of an electron pocket. So what if I introduce infinitesimally small vortex, which will be like this? Blue is here. So the second one is blue. It's a particle hole. Notice it's not a particle-particle. But let me put it in a spin channel. Let me put sigma I here, which means that fermion has spin index alpha and beta, and this sigma I alpha beta. I means X, Y, and Z. I don't care which one, but you know why? You know anisotropy of the Earth, right? Standard story. Why our world is anisotropic? You know, it's not SU2 isotropic, right? Before you kill me on this. You know why? Because magnetic field is always along Z direction. Nobody's applying along magnetic field along X or Y direction. When we say apply magnetic field, it always goes along Z. So let's do sigma Z. It really doesn't care which component of sigma we take. Very good. Now let's renormalize this, as we did for superconductivity. This is what we did to calculate superconducting susceptibility. And when you renormalize this guy, so this is the bare, we want to obtain full one, right? Full one will be equal to, I have to do it with two colors all the time. It will be bare one plus all possible corrections. What are these corrections? The corrections will be, I can do it like this, and interaction will be between these two. I put interaction with one particular color, but you understand simply because I have two hands and two colors in my hands. Or I can write down this part. Invert here, do this, and then write down it here. Very good. There's nothing else I can do. And of course, sigma, what is black? Black is here. Sigma z here. Which one is this guy in our notation? It's density, right? This lambda 4. Which one is this one?
3.
Sorry?
3.
Lambda 2.
Yeah.
2. Look at this.
Oh.
2 in, 2 out. This lambda 2. This is exactly why you have this combination. So it turns out, what it means. It means that susceptibility with respect to, what is this? This is magnetic order with momentum capital Q. This is what we normally call either antiferromagneticism or nowadays spin density wave, right? Magnetic order. And susceptibility with respect to this order will be 1 divided by 1 minus lambda 4 plus lambda 2. And then look what it have here. Particle Hall with momentum capital Q. That's precisely logarithm that we get. So logarithm. Very good. So now we know what's going on. The guy by the name lambda 4 by itself wants to create spin order. I would expect a question as a cut. Why spin order? Why not charge order? Why don't this guy wants to create charge order? What's the difference? Well, the difference with charge order is that if I don't put spin here, there are other diagrams. Like which one? Like this ones. Let's put it this way. So the spin. Now suppose that I want to try other diagram. And they will be like this. There will be interaction, and then this way. This will be other interactions. This will be, I guess, in, out, right? So this is what we call lambda 3 or U3, but there will be a bubble here, right? Each bubble will give me factor -2. Now, if I put sigma here, or I had black, right? Where's black? Somewhere here. Put sigma in black. Oops. If I have sigma I here, or sigma z, right? What this term will be? 0. Why? Because I need to sum up over spin, internal spin projection, and there is sigma z here. I get 0. So this term is not present, right? And if you would say, well, what about charge? Can there be charge order? Then forget about spin, right? Charge order is delta alpha beta. Delta alpha beta here, delta alpha beta here, delta alpha beta here. And this guy is working. And it gives me something with the factor -2. And minus will overshoot plus. So then you will see that in the chart channel, I will get opposite sign. And as a result, it will be not something like 1 minus log, but 1 plus log. This is what would happen at the end of the day. So chart channel will not work, but spin will. And with this, we can formulate, oops, we're out of time. But at least at this, we can formulate something that created a job for 1,000 people in the last 20 years. Namely, you will see what I'm saying. Let's try to read what we obtained. And what we obtained in simple words means this. The system wants the system with repulsive interaction. Let's start with the beginning. This interaction is larger than this one, so repulsion for superconductivity. Bad guy is larger than good guy. But also positive lambda 4. And now the system increases lambda 4 means that the system tends to develop magnetic orders, right? In the process of developing magnetic order, lambda 4 gets larger and changes sign of good component of the pairing interaction, right? So it means that as the system tends to approach magnetism, it creates attractive interaction between fermions, right? And of course, the words spin fluctuation promotes superconductivity is synonym to what I said. What I described is a situation when tendency towards spin order and tendency towards superconductivity are comparable tendencies, right? They're both logarithmical, and I have to, now this task that would be, if I would be faster than I'm actually going, then we would discuss interplay between two tendencies. There is now attraction in the superconducting channel. There is always tendency to create magnetism. So the question is who wins? It's a separate story, interesting problem. Answer is that for our problem, magnetism wins. But if you change problem a little bit and make hole in electron pockets non-equivalent, then superconductivity wins. The point is that you do some changes in the system. You cannot change this. In some sense, this is topologically protected. The two functions go like this, they must cross. So there must be attraction. And then superconductivity wins. But after this was discovered, people realized that there is a new concept. And new concept is this, that if the system is close to magnetic instability, then we are pretty much guaranteed that there will be attractive pairing interaction, right? And this created the whole business. Number of posters were on this. Created the whole business of what if we consider effective interaction mediated by first spin fluctuations, then in more recent years, pneumatic fluctuations. Then you can also look at loop current fluctuations, etc., etc. Which all goes with the same scenario. If in the process of creating non-superconducting order, this order promotes attraction in superconducting channel, then we can reformulate the problem and look at the problem as if superconductivity is mediated by this effective excitation, which in this respect plays the same role in phonons, but now they're collective modes of electrons. Because what is this? What's spin fluctuations? It's particle Hall fluctuations in a spin channel. What are pneumatic fluctuations? In particle Hall fluctuation in charge channel with angular momentum 2. This is what normally pneumaticity is. So this all are collective modes of electrons. And then the whole business of creating effective pairing interaction because the system is close to other instability. This analysis shows that if the system is close, if this guy is already pretty large, or suppose I start with the system close to magnetic instability, bare value of lambda 4 is already large in this case, then this effect will be huge and there will be no reduction here. It will just straightforwardly go up. So this means that we will be guaranteed then we have attraction. And then the story is reformulated different way. Does it mean that, great, we're always guaranteed to get superconductivity, we won, everything is fine? I'll finish with last phrase, no. Because if the system is close to any instability which is non-superconducting, you calculate, you ask simple question, are fermions good quantities? Are fermions good quasi-particles? So far, we assume that fermions are good quasi-particles. All bubbles that we calculated were bubbles made out of 3 fermions. But it turns out that if you are close to any instability, magnetic, pneumatic, loop current, doesn't matter which one, self-energy for fermions is singular. And then you have another phenomenon, non-Fermi liquid. And non-Fermi liquid tends to decrease all these effects. In this respect, non-Fermi liquid competes with superconductivity. If you give me 4 extra lectures, I will tell you about competition between Fermi liquid, non-Fermi liquid, and superconductivity. And with this, I guess I will say thank you very much for listening.
Yes. So for the diagram you had here, there's an L star where lambda 1 and lambda 2 meet, right?
Uh-huh.
Now, this also means that there's an L value where lambda 2 will cross 1 because it's increasing.
Is it sorry?
The lambda 2 will cross 1.
Yes.
Increasing.
Yes.
So does this mean that we are out of the?
It's a good question. It's a good question.
4.
So
Crosses one first.
the story, sorry?
Sorry, unless lambda 4 crosses 1 first.
Yeah, yeah. So
Maybe.
basically, the story goes like this. This is what is called one loop RG. With one loop RG, you start with small values of the coupling and see how they evolve. And you stop your RG when coupling becomes a order of 1. And then the only question to which you can answer is which tendency is the strongest at this scale. And it's believed that if there is no situation when there is a degeneracy, when you really don't know what's going on, if you find coupling that is already stronger at this scale, then this is what comes out. Maybe I can show you one slide, one plot here. If you don't, right. I'll show you this plot. These are equations. Ask Mathematica to solve them. Mathematica will solve them for you. Now, what I will do is this. I will plot 2 quantities, both as a function of L. Both will start with the small values and then will grow. One quantity is superconducting, which is lambda 1 bar minus lambda 2 bar. Oh, let's put it a different way. Lambda 2 bar minus lambda 1 bar in order to put everything as positive. So positive means attraction. Yeah. We start with the negative value, right? And then we go like this. Where do you have to stop? 1, 1/2, I don't know. You cannot go here, right? Let's look at another quantity. This one. Tendency towards spin density wave. You start with positive value somewhere here, right? You don't need. Beauty is that magnetism comes from repulsive interaction. Stoner criterion is for repulsive interaction. And then it also goes up. They tend to come closer to each other. But of course, you have to stop. And then if you stop somewhere here, you can say, yeah, tendency towards magnetism wins. This is what I said. If hole and electron pockets are identical, magnetism wins. Now make hole and electron pockets non-identical. What happens? This guy, this red guy, will not continue growing. You cut up logarithm in a particle hole channel. When size of hole and electron pockets are not equivalent, logarithm is not exact. That means that you cannot extend logarithm to the lowest possible frequencies. Which means that when L formally goes up, this guy saturates. This guy continue growing. And then you see what's going on. If it saturates at a value lambda smaller than 1, superconductivity wins. Right? Again, you cannot say that it wins definitely. You stop here. But there's a, people try to do two loop calculations to extend this a little bit further. If you have 4 couplings and you want to do two loop calculations, I suggest not to do this. Because it's really very subtle calculations, and with 4 couplings. Yeah, but I hope I gave the answer. Yeah.
Yes.
So, lambda one, the way we had defined the lambda parameters, lambda one and lambda two were proportional to U1 and U2.
Yes.
And we have been seeing that when the interaction is between pockets, we have larger U than inside a pocket.
Mhm.
Why is lambda one greater than lambda two?
No. Their interaction. No, they're two different things. When you say that lambda 2 larger than lambda 1, I already included conlatin normalization. This, as I said, first order solution of these equations is conlatin normalization. So when you talk about bare values are before any renormalization. These are your interactions. If you start with Hubbard U, then as Nikolai says that lambda 1 and lambda 2 are the same.
Yeah.
Then here you start with 0. But you can start with negative values. This is what I mean.
Okay.
You can say that, well, let's be realistic. Interaction at small momentum transfer is always larger than interaction at large momentum transfer. So you start with repulsion. What RG allows you to do is to see how initially repulsive interaction goes into attraction before it hits once.
Why are we flowing to large L instead of small L? Why are we flowing to large L instead of small L?
Because we are flowing to smaller and smaller energies and temperatures. And the less smaller is energy, omega, the larger is L.
So we're not renormalizing the cutoff, we're renormalizing.
We're normalize frequency, yes.
Okay.
Yeah. No, we don't normalize anything. It's RG in the purest possible way. It's just a way to sum up logarithm. We are not doing shell RG. No, we are doing simple calculations. So here RG is really the way to sum up infinite series of logs.
Do you get the same result if you think about it in a shell RG way?
Of course, you get the same result, yes, in a shell RG. But
Would that be?
the problem with shell RG is the problem with any RG of this kind is that when you do shell renormalization, you start with bare coupling. You do a small renormalization of the shell, and then suddenly you replace bare coupling by a running one. And this is accurate only if the theory has logarithms. If the theory has no logarithms, you can still do it, and people do this, but then it's just like you do uncontrolled approximation. Sometimes it works, sometimes you get physically meaningless result, but there is no control on what you are doing. You are doing uncontrolled calculation. In this regard.
I have a follow-on question.
Yeah, sure.
Suppose I want to be fancy, I want to go beyond one to follow following like this question. And but it's like, how do you change your ansatz of your differential equation? Because like otherwise you put like L squared in the denominator, right? Because you have to lose.
No, what, two
lambda
loop means that you have L cube terms here.
Yeah, exactly. You have lambda cubed, right?
Right.
Then
Yeah, lambda cube.
Yeah, but how would that change your ansatz of your solution?
Which ansatz?
Like lambda is a function of previously you put lambda equal to.
Oh, no. Just 1 second. I try to understand very quickly what you are asking. We're talking about this scale or about this one?
No, I mean lambda bar as a function of L.
Lambda bar as a function of L will be as long as what happens as long as these guys are small, cubic term is irrelevant, right? Cubic term becomes relevant here when coupling grows. You need to check that it continue growing, that there will be no crazy stuff going on, that it will not suddenly return back. Yeah. Or saturate.
In that case, it's hard to write down the answers like 1 minus lambda L.
No, you cannot do it. Yeah, because again, you can do it as long as there will be terms lambda square times L. And as long as lambda are small, then yeah.
That's it. So let's thank Andrey again. Thank you.
Then 24 minutes of break, and then we start your presentations. And there will be 3 groups. You decide how you present, you decide who will present. Everyone will be involved in the sense that everyone will be asking questions. The task of everyone else, of course, find mistakes what you are doing, obviously. And then half an hour per each group, right? So hour and a half total. Okay, good. Order will be group 1, group 2, group 3. So Daniel group will start first, then Nikolai group, and then my group.
Response to the reviewers. Usually I just added one extra paragraph and they're like, okay, yeah, sure. Except for the review from Cal.
Yeah, so the only difference between the solution to part 3 and the solution to part 5, where we add this in one term, is that we have this h dot sigma z term inside the square root.
Why are we keep this three? I'm thinking the other components.
Oh, you might have taken the Zeeman field in the sigma z direction.
No, I think I put all the components in the Hamiltonian. So, for example, here.
Last one is presented, Grayson.
After my solutions, so I need always
Yeah, so I wrote it. It was H things, now these things. Then as you pointed out, H Y out 0.
Yeah, but I have one bit.
H C plus E sigma Z. Delta K minus
We will go add
L Y. Yeah, that's what.
And then for the Q parts, like the odd part, wait, was this asking for the odd part?
I think I started without any Qs. I just was Q can be added by.
Worst comes worst, we just write down that Hamiltonian and say there's. Just.
Yeah, but I think.
Like even, or even like if you all the Q parts are even more, any time on, so they should.
Yeah, but the one in the notes that you have to use.
So this.
But yeah, we.
So it had an H plus field. Yes. So you have that and there's that.
This is perfect.
Oh, you want to do it now? Ask for me. I think we're not.
Oh, okay. Oh, I get all of that. Thank
I mean.
In general, be a modulus of this document.
you square this up. So you have cross terms between the deltas and the H's as well, don't you?
And there's, yeah,
Okay, but obviously you could have cross terms to the deltas as well.
But this is
I think because these terms will go like not answered. And so will the other two actually.
Okay, so what will be the actual final session? Where everyone's going to present the result of the homework problems.
So the way it would work, just as a reminder, is we're gonna have half an hour, where you guys all present your results. And we just ask the audience, please interrupt if there's something you don't understand, or you're saying unclear, really please, just ask.
We're only asking questions,
Yeah,
even if everything is clear.
okay. Yeah, and okay, so then we'll start with, since the board is cleared off, we'll start with, group one, have your, representative, or again, if there are multiple representatives, however that is organized, please come up and then present the results.
Can you project the question on the slides dimension?
Maybe.
We don't have questions. So,
Can you give me a question?
TD and then I gave a easy TD, I did the thing. I think I can put this.
Great. Okay.
Okay, so the first problem. Okay, so the first problem for
turn
the.
it on.
Yeah, at the top.
At the top. Yeah, now.
Yeah,
it's
I
on.
guess this is fine. Okay. So the first part of the question deals with dealing with normal state Hamiltonians which have broken time reversal and inversion symmetry, but they still satisfy the Kramer's degeneracy principle of Ti square is equal to -1. So the example which was dealt with us in which was dealt in class had both time reversal and inversion symmetry. So and there we had seen that the normal state Hamiltonian was completely symmetric, and one of the examples was cosine kx plus cosine ky. But in these systems where we have broken time reversal and inversion symmetry, even in the normal state, we can have any combination of a symmetric and an anti-symmetric term. So without making any assumptions as to what the form of the normal state Hamiltonian will be, we can write it as epsilon q as epsilon 0 as a function of q, which is the symmetric part. So, and then epsilon minus as a function of q, which will be the anti-symmetric. In which case, my BDG Hamiltonian, which in its general form is Hn of k, delta q as a function of k. So I'm not worrying about the q dependence as of now. It comes up in the later part of the problem, but initially we assume there is no q dependence. Delta as a function of k transpose and minus Hn transpose as a function of k. Okay, so if I substitute this form of the normal state onto this Hamilton, each one of minus. Yeah, so this becomes epsilon 0 as a function of k plus epsilon minus as a function of k, delta of k, delta dagger of k. And here, since this is symmetric part, I just get 0 as a function of k. And since this is anti-symmetric, epsilon minus of minus k would be minus of epsilon k. And with the overall minus sign, this shows up as. Yeah. And now we just diagonalize this Hamiltonian, similar to the form of Hamiltonians we have seen a lot during the summer school. And we basically get the eigenvalues as, so this is the part we are very familiar with, epsilon 0 as a function of k square plus delta k square mod. But we have an overall anti-symmetric part outside the square root, which gives us the two eigenvalues of this Hamiltonian. Okay. So this was, so in part one, how does epsilon k differ from both T and I symmetries? It's the presence of this term, which makes it different from normal states, which have both T and I symmetries. And how does the quasi-particle excitation look like? It looks exact, the quasi-particle eigenenergies are this. We have not made yet any assumption as to the form of what the order parameter is. It can be singlet or triplet, which is what the question asks us. Either it's pure singlet or a pure triplet. No, there is no mixing between them. Okay. So now I write a more general form of the BDG Hamiltonian with the Q terms in it, and we try to expand it. So the normal part of the Hamiltonian is H and K plus Q over 2, which I can expand as Hn as a function of K plus Q over 2 dot gradient of Hn as a function of. Similarly, I will have a similar term on the other diagonal, and for the order parameter, these are just delta Q, okay, and delta Q. Okay, so now taking this particular form of the eigenenergy and substituting it in place of Hn of k, we get, so I'm just writing the diagonal terms here. The off-diagonal terms, they don't concern themselves with the normal state properties of the Hamiltonian, so I'll just keep them as delta q as function of k. But the normal state basically becomes epsilon 0 as a function of k plus epsilon minus as a function of k plus q over 2 epsilon 0 prime as a function of k plus epsilon minus prime as a function of k. And then the other diagonal element is just minus epsilon 0 as a function of k minus epsilon minus as a function of k plus q over 2 minus epsilon 0 prime as a function of k plus epsilon prime minus as a function of k. Now, the way we get this expression is that if we have an even function, the derivative of it should be odd. So epsilon 0 is an even function. So epsilon 0 of k is epsilon 0 of minus k, but epsilon 0 prime is an odd function. Therefore, when I do the minus k substitution to get the other term in my Hamiltonian, this term in the Hamiltonian, I get a minus of epsilon 0. And similarly, epsilon minus k is anti-symmetric, therefore it gets a minus sign, but the derivative has a plus. And then we do the same procedure as we did to diagonalize this Hamiltonian, subtract lambda from the diagonal elements and find the eigenenergies. I'll just write the form of the eigenenergies we get. Lambda is epsilon k plus q over 2 epsilon 0 prime as a function of k. Whole square plus. So this is the general form of the eigenenergies which we get after we do the q substitution, after we have a finite q in the momentum and taking the both symmetric and anti-symmetric part of the normal state. Now for part 4, I would like to call Patrick on and he'll be able to show you guys and draw what the nodes look like when you have kx square minus ky square gap on a circular Fermi surface.
So maybe I'll make a comment here. There was a physical reason I asked for this question. So your answer is completely right. So you notice in this eigenvalue, you've let epsilon minus plus q dot this derivative of, so it's the velocity, right? So you have epsilon minus plus q vf. Many people study the superconducting diode effect where there is this finite q. But what you can see from this is that finite q in principle can couple to terms like epsilon minus. And so these superconducting diode solutions can generate other terms in your Hamiltonian that carry that same symmetry. So it can create other fields that are time reversal odd, inversion odd, but preserve their product.
Okay.
So you can get these interesting situations where maybe a supercurrent can create anti-ferromagnetism or something like this. That's what this equation does to it.
All right, so the next part of the problem, we're making a couple assumptions that allow us to simplify the form. That allow us to simplify the form of the eigenvalues we have here. We're assuming it's a circular Fermi surface. And we have the kx squared minus ky squared gap. And we're assuming the q is just along the diagonal with qx equals qy. So we can simplify it a little bit. We end up with the form, and we can also just sort of assume that kf equals, or kx equals k Fermi cosine theta, and make the same substitution for y. We end up transforming this into the form lambda equals q k Fermi cosine theta plus sine theta plus or minus k Fermi squared. We're assuming we're at the chemical potential. Cosine squared theta minus sine squared theta squared. So it's just the absolute value. And you can see some nodes immediately at 3 pi over 4 and minus pi over 4. So on our Fermi surface, we immediately have nodes here and here. The other nodes are a little bit more complicated, and so the easiest solution we found was to do this graphically. So if we take this function and we just plot it.
This is just sine plus minus cosine, right? Sine to theta plus minus cosine to theta.
Oh, that's one.
Yeah. I found it more straightforward to solve it graphically. Some other folks did it more analytically, but yeah.
I just want to make sure that this is what you have.
Yeah. So ky kx. So this function looks like sort of 4-leaf clover. And this function just draws a circle that intersects with the 0. And there's 2 branches, so you end up with 2 circles. So we also see this solution at 3 pi over 4 and minus pi over 4, where the circles intersect with the diagonals of this function. And then the other zeros that we see are like off the 45 and 5 pi over 4 lines here, off the 45-degree lines. So the effective Q is essentially splitting the node from here to these off diagonals on both sides. So those are the locations of the nodes that we found with the non-zero Q in first order.
That's good. But now I want you to imagine what happens if you included your chemical potential. What might happen around where those nodes split into 2? So I don't think you've solved it. So you have 2 possibilities.
I remember with the chemical potential, the figure sort of looked like this. And then the solutions were here and here. So unless you had like large Q, I think the solutions went away, right?
Okay, yeah, if you make the chemical potential large, but actually so you've thrown away the term that gives you the Fermi surface. So there is another term there.
Okay.
That term can be small. So we usually have epsilon squared plus delta squared. The epsilon can vary from 0 to something large. And what you showed there was for that epsilon large.
Mhm.
But it turns out, so I'll just give away the answer. I don't know, does anybody know what happens if you go off the Fermi surface in this particular picture? Does anyone know the answer? Okay. So what actually happens is you get a Bogly-Bott Fermi surface. And you get a Bogly-Bott Fermi surface whose zeros move off the chemical potential and form a Fermi surface along the ones where your two nodes split, and then these other nodes stay in place.
Okay.
And the only way to see that is if you take mu, the epsilon square term sufficiently small that you can see that as you move off the chemical potential, you can see that that node still survives and that node moves around and completes a Fermi surface.
So I think what we do also at the Fermi surface, the normal state epsilon 0k minus mu part, that should in principle be going to 0, right? If I have epsilon minus set to 0.
Yeah, so what you saw was on the original Fermi surface, everything was correct. And then to go further, what you should have considered what happens as you move off the Fermi surface and you stay close to it. So you should have looked maybe near that, still where the node split in two. What happens as you move off the chemical potential, and you'll see that the node still survives and it forms the Bogly-Bott Fermi surface.
But the problem says don't do it.
No,
It says don't leave it. You say epsilon has to be 0.
no. Epsilon minus is 0.
Yeah.
So so all you're doing is adding this to a normal D-wave superconductor. And again, this problem has been studied in the past in the literature. And the main place it was studied was for D-wave superconductivity coexisting with a loop current state. And then you get Bogly-Bott Fermi surfaces. And people propose that these Fermi surfaces might give you de Haas-Alfvén oscillations, and that may explain what was seen in an experiment. That turned out not to be right, but that was the original motivation.
Okay, so for the last part of this problem, we add a Zeeman term onto the Hamiltonian. So just to remind you guys, we had a form of the Hamiltonian after the finite Q and having the anti-symmetric part. We had the normal state epsilon 0. I'm writing it in a very shorthand notation, getting rid of the K dependence and everything, but we had a Q over 2 epsilon 0.
Make it even smaller.
Okay, so this is the general form of the Hamiltonian we had with the K dependence everywhere, with the K dependence everywhere. But now the idea is that what happens when we add a Zeeman term. So one thing, the BDG Hamiltonian is a 4x4 Hamiltonian, but the way this is written, it's a 2x2. So there is in this the way we have formed this Hamiltonian, there is a tau 0 term missing. And this is a 2x2 matrix, this is a 2x2 matrix, and the form of this 2x2 depends on whether you have a singlet or a triplet. And in our case, in the example that we have, it asks us to show it for a spin singlet case. So you just have the I sigma y form of the order parameter. What happens when we add the Zeeman term? So the Z-man term, H dot sigma, H dot, let me be precise. I have and then I add H dot sigma term, and for the other part of the Hamiltonian is minus H dot sigma. And then the idea is to base it, so we are keeping a very general form of the direction of the Z-man field, not assuming it to be along the Z direction. You can, but if you have this particular form of the normal state Hamiltonian, and then you try to diagonalize it, the only difference we see from the solution that we have gotten here is that when we have the Z-man term, we get a mod H dot sigma square term inside the eigenenergy. And that's more or less the only difference we observe when we have the Z-man term and when we don't have the Z-man. Inside the square root, we have an H dot sigma term coming because of the Z-man.
Well, I'll disagree. Yeah. So what you should get is you should get a plus or minus absolute value of H plus the epsilon minus term plus or minus the square root of epsilon squared plus delta squared.
So the H term should instead be outside the.
Yes, it should be outside and there should be a plus or minus in front of it. Yeah, I mean, this was a lot of algebra, this question, so I realized that, so.
Yeah.
Okay.
Yeah, because I think.
Zero.
Sorry?
Put delta to zero. And then immediately you will see that H should also affect terms without square root.
Yeah.
Yeah. So maybe I'll point the main message from this. Whenever you get this form.
Yeah. If you don't mind, go there with microphone because. Why?
All right.
There's a second microphone if you want.
No, it's fine. Yeah, so the main point was whenever you have this plus or minus this, one of the things that jumps out all the time are Bogdanov Fermi surfaces. All right. So if you ever see this form, this plus or minus this, you'll get that. And if you have a D-wave superconductor in a Zeeman field, you'll find that the nodes in the D-wave superconductor become Bogdanov Fermi surfaces because you have a plus or minus of H part here. So I think we only have a couple minutes left and we have still 2 questions.
These ones are fast.
Yeah, the second one should be relatively fancy.
That one from the second part. Maybe we started in the last 5 minutes.
Yeah, that's what this is.
The second problem also works too.
Second problem.
Oh, sorry,
Okay.
sorry.
Already. So for this second part, we're looking at this tenfold way. Like so we're looking at class C2 right now, and so for class C2, I'm going to write down. So remember, we're considering a local symmetry when it leaves K invariant. There was 3 possible in this configuration. So we had this charge conjugation times inversion, which is anti-unitary. We also had time reversal times inversion. And also lastly, the chiral symmetry, which is unitary, but this charge conjugation times time reversal. For C2, this -1, and it does have this chiral symmetry. And so we're considering specifically a spin triplet. So this is a bit different from the discussion in class. So in class, let's first just write down what the representation of these 3 like local symmetries are, like for this like spin triplet. So first, there's a time reversal, which is just going to be just the usual I sigma y So let's product that with tau naught, and this is anti-unitary, so it's also going to be some complex conjugation. So this is the matrix representation. The second part is going to be, I'll do this inversion by itself. So this is the part that's a little bit different. So if I write down the BDG Hamiltonian, I have, of course, I should make sure I'm not covering it. I have the normal part here, normal part transpose minus, I'll leave the K, the minus K. And so now, before we have a spin singlet, and so remember I'll say spin singlet, these are even partial wave channels, they're even under inversion. So this is going to be, I sigma y, delta K, where delta of K is equal to delta minus K. Whereas if we have a spin triplet, I'll say it is described by a D vector, and these are odd partial wave channels, so it means it's odd under inversion. So we have, I'll take the convention that we have a D of K dot sigma I sigma Y, where now this D of K satisfies D of K is equal to minus D of minus K. And so before, when we had spin singlet, if I were to take this BDG Hamiltonian, take the inverse, you'd have this delta of K is equal to delta minus K, so X trivial on this BDG non-boost space be tau naught. But now since I have this, I'll just write triplet for brevity. I have this triplet order parameter, which is odd under inversion. So in fact, this inversion acts non-trivially on this particle hole space. So in fact, the inversion is actually going to be a tau z in the particle hole space. So it's going to be tau z and X, or sorry, like I'm gonna actually, for notation, I'll switch these two around. I'll do a particle hole first, and then spin space. Kind of keep it consistent with this. So we have tau z then times X trivially on spins. And the last one is charge conjugation, and this is the same as for the S-wave case as we discussed in lecture, which is just going to be tau X complex conjugation. And so you can likewise, just from these three representations, of time reversal, inversion, charge conjugation, you can write down these three local symmetries. So Ci, I'll just write it down real quick. So just a quick exercise of Pauli matrices. I have then Ti is minus I tau y complex conjugation. And lastly, I have my chiral symmetry, which I'll just write as S, which is like brevity, which is just going to be I tau z sigma y complex conjugation. And so now we have this, and so we'll kind of do a similar scheme. I'm doing time. I should hurry up a little bit. We should do a similar scheme of how we would find out. So you could start with, for example, everything that satisfies this chiral symmetry. So it means it has some, if you write down our Hamiltonian, so as just, well, actually, yeah, like I won't do that. But basically, Hamiltonian is going to consist of always going to be like some Cij, I'll say some tau I, tau j, sorry, sigma j, where Ij is equal to 0, 1, 2, or 3. So in order to anti-commute with this chiral symmetry is tau z sigma y. So I could have, for example, I could have a tau x sigma naught. I could have tau y sigma naught. Or I could also have, if this is sigma y, I could also still have tau x tau y. And I could also do the same for the, now I could have instead tau naught, or tau z. And I'll just write them all down. These will use them on the next problem as well. So yes, so if so we have tau naught, so we can have a sigma x or sigma z, or you could have, if it's tau z, likewise you could have sigma x or sigma z. And then yes, and so from this, we would look at how these operators behave under this charge conjugation inversion and time reversal inversion. And so basically like Like you just kind of go through all the math at a given time. I won't go through each one. But what we find that survives is the tau. Let me do another color. Is this the tau y survives? We also have tau z survives. Somewhere here. Did I rewrite it somewhere? Tau z, tau z. Wait. Sorry. Did I rewrite? I might have written this problem wrong. Oh, I'm so sorry. I misread my handwriting. The chiral symmetry is tau x, not tau z. Oh my gosh. So in that case, so basically, if that's tau x, switches all these x's to z's. Otherwise, everything is the same.
So maybe, just to save time, can you write down the final dispersion you get?
Sure.
And then go from there. Because I also noticed that your CI and your S, the complex conjugation operator should be on the top, not on the bottom. Because.
Oh, yes.
Yeah,
Sorry.
yeah, so, yeah.
As this writing, I must have, that's probably where I. So let me, so it should be CT is T.
But I think.
No. So this is my S.
Yeah, okay.
Yeah, so that's my S. That's where
Okay,
that's where I got mixed. Yeah. Okay, so this was tau z. I was just looking at. Oh yeah, so this is my TI. Oh yeah, thank you. Sorry. Oh my gosh. I should do it on the board, not read my handwriting. So that's more consistent. Yeah. So this is consistent. Yeah, so all of these are correct. Then you just should actually do it as opposed to read your messy handwriting from last night. And so yes. So our final Hamiltonian then, I'll just write it down.
Final dispersion, yeah.
Square roots of all of them.
Yeah.
Oh yes, let's just write down like, so I can just have I'll say it's a C like a y0 at tau y, plus C z0. Like these are functions like of tau z plus I'll call it xx, tau x, sigma x, and then lastly T plus C xz, tau x, sigma z. And so you could just play the trick. You can take this squared. And so you can get your dispersion. You'll have this like this C term. Like this commutes with everything on the right-hand side. And so these actually all like mutually commute. And so we're good. So you'll have like a cy 0 squared, cz 0 squared, cxx squared, and cxc squared.
That's right.
And that will give you your dispersion.
Yeah.
And then, yeah, sorry for the little typo. Then I can send Andreas for part B. Like
So, but the main point is, why does that not allow you nodes, that dispersion?
Oh, yes. They were doing the put dimension. Yes. So basically, if you look, we have total of 4, and it's basically a system of equations. We have too many parameters. Okay, so similar to when we had when we do this dispersion in class, we had 3, and if we had 2 parameters, it could give us a line node. In this case, we have a 4, so it's basically too many parameters, so we can't have any nodes that has to be gapless.
Yeah, okay.
And then I can send it to Andreas. I'll grab it.
So maybe we'll do this. Maybe this part gets answered, and then we switch to Nikolai's and Andrey's, and then maybe we do my third question if there's still time. Does that sound reasonable?
Okay. So just give a quick sketch of your solution. No.
Sure, like part B doesn't have actually too much in the way of algebra, it's just in the way of reasoning. So, okay. So part B tells us, okay, what do we do in the case of A2? And A2, just to repeat the conditions we have here, has no CI, no TI, but still has S. So the point is we need to write the minimal Hamiltonian which violates both CI and TI, but still maintains S. So as a starting point, we wrote these 8 here, which all are guaranteed to have S. So you might say, okay, let me write a Hamiltonian which has all 8. And that linear combination will break CI and TI, but that's definitely not the minimal model. So what's the trick we can use now to find the minimal model? Okay, you think, okay, let me just write 1. Let me just start with 1 and see what happens. And using these CIs and TIs, you might be able to find one, which in this, for this particular form of CI and TI, it works. But you have to make sure that for whatever representation of CI and TI that you use, that it's always going to violate CI and TI. So for example, these CIs and TIs that we have both squared to -1 and -1, but we could have just as well chosen ones that square to +1 and -1, or both +1, one of them -1, the other one +1. So to prove this rigorously, you'd have to use some pure maths. But if you're just going at it, you just pick any two, you take a linear combination, you find that that linear combination together will break both CI and TI. So just to show you that a bit explicitly, so the choice is not unique, but the point is you need at least two. So let me see. Yeah, so the linear combination we found,
So when you say 1 and 2, that's the number of basis states.
sorry, what do you mean?
So you said we can do it with 1.
Yeah, I mean, sorry, I just meant with one term.
One ice.
Like one choice of these terms, but I'm saying we need at least two. Yeah. So, okay, let me write it over here. So the choice you can make is the following. Again, this choice is not unique. You just need to find two that break them. So we just decided to choose a case where epsilon k is odd, just to make it a bit more concrete. Okay, so I realized in writing this that it's a slightly disingenuous choice because this one doesn't actually have any superconductivity. But as far as just doing it purely mathematical to make the point clear, you can see that sigma z and this tau z sigma y will always transform differently, or at least as a linear combination, they won't transform correctly together as something that transforms right under CI, under TI, regardless of whether you find a CI that squares to ±1 or a TI that squares to ±1. So that's the general message. I mean, it's just a bunch of algebra to go check that for yourself. But the point is, just in this particular concrete example, okay, these terms mutually anticommute, so you can write it as a square root of the sum of the squares. And again, we have two constraints on a system of 3 variables, so that means we can have nodal lines. That's the ultimate message. Oh wait, I should have called this 1 and 2. My bad. So yeah, I hope that's.
Yeah, so that answers it. There is a way that is a little quicker. So you can realize that when you have broken inversion symmetry, your TI, your pseudo-spin degeneracy is broken, so you don't have a spin degree of freedom anymore. And so you can throw out that twofold set of degrees of freedom, and all you're left with is the charge conjugation operation. So you only have particle hole in your Hamiltonian. So what you can just say is, let's just start with the particle hole symmetry tau x, and then write down all possible Hamiltonians expanded in particle hole space. And then you can show that only 2 terms survive in that expansion because it has to anti-commute with tau x, and so there's only 2 operators that do so. But in the end, your logic leads you to that, but in a less direct way.
Right. Okay, thank you.
Okay, let's thank our and then let's have the representative from group 2 come on up.
Because you also need to slow down, right?
Yeah. Okay. Maybe that's you just put here.
Let's see. How do I make it?
Full screen?
Let's click F.
Oh, and the pseudo spins over just so people.
Yeah. There's a full screen in the upper there.
Yeah, no, this is already full screen. Yeah, doesn't matter. Okay. Yeah, hi everyone. So I will present our results for the homework for group 2. So to make a good use of time, so I type everything into this PDF, and you can find this PDF in the Google folder where you upload your slides. Yeah. So so here I will just walk you through the derivations, and if you have any questions, you just interrupt me, and I can do the more detailed derivation on the whiteboard. So the problem is here. So we consider two separate S-wave superconducting mechanisms and compute the corresponding critical temperature for them. So here we assume the simplified model. So the gap function is only frequency dependent, and we also replace the Mossbauer sum by this integral from T to the Fermi energy. And the two mechanisms we are considering is one is for mechanism A, the gamma function is 0.25 inside the small square and 0.5 outside this small square. And for mechanism B, so inside is 0, outside is minus 0.15. And the second question is to calculate the general analytic expression for the largest eigenvalues and plot the relation between it and the log t. Then the third one is we combine these two mechanisms together and repeat the calculation. So in the following solution, I just for simplicity, so I just denote this square EF divided by 100 by capital omega. And firstly, we consider. By the way, can you see that clearly? Okay. Firstly, we consider mechanism A, and we divided the discussion into two cases. One is omega less than capital omega, and another is omega bigger than capital omega. And for the first case, we found that the integral on the right-hand side can be split into two separate parts. So the first part means both omega and omega prime are inside the small square. Then the gamma function is 0.25, and the other is 0.5. And the key observation here is we found that the right-hand side does not depend on omega. So that means this omega, as long as omega is less than capital omega, this delta function is a constant. And we just denote this constant by delta 1. And similarly, we can find that the gap function for omega bigger than capital omega is another constant, delta 2. And then you can rewrite this function equation 1 into this 2x2 matrix. And because in the first problem we are considering the critical temperature, in this case, eigenvalue is equal to alpha equal to 1 is a solution. So we just let the left-hand side equal to 1, and then we will get two relations between delta 1 and delta 2, and then make them consistent. Then you will find that the critical temperature is this value, about 3.94 by times 10 to the minus 7 power times the Fermi energy. And we can repeat the computation for mechanism B. So basically this prefactor is changed. Here is 0, and this is 0.25 of these three elements. And then we can also repeat the calculation, set alpha equal to 1, and get the critical temperature equal to about 4 times 10 to the minus 4 power times the Fermi energy. And the second problem so asks about the analytic expression for the maximal eigenvalue. So we just use what we learned in the first year linear algebra courses to set the determinant of this matrix equal to 0, and then we solve the quadratic equations and find the zeros. Basically, we will find two solutions. One is plus and one is minus. And the maximal value, of course, you should take the plus sign. And
this is the plot for alpha max t versus log t. So it looks like this. So as you can see, as temperature decreases, then it will cross 1 at about log t equal to -10. So that means at this point it will have superconductivity. And similarly, we can do that for mechanism B and plot function like this. And it will also have an intersection with y equal to 1 at about -3 here. And finally, we can combine the, for the third question, we just combine them together. And then we will have another 2x2 matrix. And we can also solve the maximal eigenvalues, which will look like this. And yeah, look like this. We have found that as t, you can see here, I already like that to be very, very small, but it still cannot reach to 1. And more rigorously, we can prove that firstly, this curve has negative slope. That means its maximal value will be obtained at log t equal to -infinity, or at 0 temperature, in other words. And you can use Taylor series expansion of the square root, and then you will find the maximal value just 0.645 is still less than 1. So the critical temperature does not exist. Yeah. Do you have any questions? Maybe another comment is, as Professor Chubukov has said, so this mechanism is very complicated, even if both mechanism A and B can have superconductivity. But if we combine them together, maybe the superconductivity maybe not exist.
Yep. I mean, like, how do I understand it physically? Just live with it. Have an exact solution, so
yeah.
New mechanisms can kill the superconductivity. Yeah. Okay. Let me ask you the following question. You have matrix A, the largest eigenvalue has microphone. I'm loud enough.
It's for recording.
Yeah. Just by pure math, suppose you have one matrix, the largest eigenvalue has an eigenvector. You have another matrix, the largest eigenvalue has yet another eigenvector. What happens if I write down the largest eigenvalue for the sum of two matrices? Simply mismatch between the eigenvectors can be such that the largest eigenvalue simply drops to some small value. Because what's good for one matrix is very bad for the other one. And so the eigenvalue for the sum can be much smaller or just more or less unrelated to the largest eigenvalue of any of them. Okay. Well, okay. In quantum mechanics, we know many things about non-commuting matrices. So that's more or less what happens here. So you have an equation, but behind this equation is a solution which changes sign and has a 0. You have another solution which doesn't change sign. But once I combine the two, what's good for one is very bad for another. And at this point, simply the largest eigenvalue can never reach 1. But literally, you have to read it properly. So when you combine two mechanisms, don't expect that UTC will go up. Not necessarily.
Right. How do you make sense of mechanism A physically? When one says an attractive interaction leads to a bound state, classically, no one bats an eye.
Sorry.
How does one make sense of mechanism A physically? For an attractive interaction, it's not surprising that there's a bound state instability. But for a purely repulsive interaction, albeit one that's dynamic, what's the classical or physical intuition for why this is still it's an instability?
I think it's just analytic result of this result. Right.
Can you explain the word classical?
Well, I guess I just mean that we can get this even in this BCS or mean field-like scenario. So there's other physical embellishments one can consider that makes it seem more physical and see an intuition from that. But we see it even at this level of analysis. So
Can you solve 2 by 2 and then transform it into only low energy part, eliminating the high
that's what we
energy
did
part?
already. Well, if you don't accept this as an answer, there is the following blah blah about electron-phonon interactions. It's frequently repeated, not a computational tool, but I don't know how reliable. One electron goes and polarizes the phonon medium. So the lattice is distorted, you gain a little bit of energy, but the electron is fast and goes away. But the second one can follow and enjoy the polarization. It's like, I know, positive trail or attractive trail left behind. Better than if you stay far away. Now, if you have retardation, and it says, okay, well, interaction is weaker at low frequencies. Well, the first particle comes, what we call screening is polarizing and pushing other electrons around. So they already kind of give way to the first one, but it goes away. And if the second one follows quickly enough behind it, it will eject. So if you like it kind of in this physical sense, yes, but strictly speaking, I would say whenever you do renormalization of interactions, nothing is kind of classical in this sense. I don't know, that's why I'm saying, okay, what is the word classical? Because classical is a strange, a little bit term though in this context. Yes, in frequency space, we have retarded interaction. So you don't think about all of this as instantaneous potential. Because when you think about pairing with a given potential, it's instantaneous. At all times, you're coupled by the same potential. That's precisely what is not happening here. It's different in frequency. And that's why it has no projection of how you pair for the instantaneous. That's. Thank you. And it's not a pair, it's a pairing correlation.
Okay, yeah.
Well, I actually have a question for Professor Prokofiev. So, what we learned from this homework is, if you have, so actually in real materials, we know that if you just have electron-phonon coupling, you might have some superconductivity. So if you only have Coulomb interaction through some screening or Friedel oscillation, you can still have some superconductivity. But in real materials, we have both. So is that some possibility that because we have both, so the TC is so hard to get higher?
One of the cases. Why not?
Any more questions? Okay, if not, then let's thank our presenter. Yeah, let's have the representative, first representative of these three come up. Yeah. Do you need any projectors or anything?
No, I just have like.
I'll just put them all.
Screen off.
Yeah, I just choose.
One.
No.
Okay, hello. Basically, we had to investigate whether there is a Kohn-Latinger superconductivity mechanism in a two-dimensional system with quartic dispersion. So alpha k to the fourth. Yeah, alpha greater than 0. Yeah. So we do the same procedure, and basically the problem that we need to investigate reduces to calculating a bubble. Let us write this particle Hall bubble. Yeah, I have it written here. So this is just dk squared integral omega m. Yeah, we're calculating the static bubble at some momentum q, right? The question is like how to compute it. Well, it turns out that you can easily perform the Matsubara sum and get the relative the well-known expression. Squared. Okay, so these are just the Fermi functions. Next, like
Summation rather than integration.
Yeah. Well, you can perform integration, you perform summation. Yeah, here we'll be considering the zero temperature limit. Then, like the expressions simplify a little bit because like the Fermi functions can be expressed through Heaviside theta functions. And yeah, at zero temperature, after like some shift of variables, it can be written in a much better form. Okay, t equal to 0. P of q equal to.
Are you sure about the sign?
Here?
It depends on definition of.
No, it's already written to the left.
Ah, yes, sure.
I think
Your sign is right.
I think I am sure.
We'll have g of k minus g of k plus q divided by their energy difference. But the sum of g through Matsubara frequencies, that's the occupation number.
Uh-huh.
Good, fine.
Okay, then it's minus.
Yeah, very good.
Okay, yeah.
Good.
Should we have a plus I0 plus, or is this just the principal part of it?
Sorry?
Is it just the principal part of the?
Yeah.
Here.
Everything will
G is 1/2 minus.
properly. Okay. Yeah, so after like a tiny bit of algebra and like doing like a change of variables, we get like the final expression that we will actually be working with. Pi squared theta function of k Fermi minus absolute value of k times 1 over epsilon k plus q minus epsilon k minus 1 over epsilon k minus epsilon k minus q. Of course, vectors here. Yeah. Now, the only thing that's like left to do is plug in this expression into this bracket, simplify it, and we're gonna get what looks somewhat complicated to compute. D phi from integral from 0 to k Fermi k dk over 2 pi squared 1 over q squared plus 2kq cosine phi and 2k squared plus q squared plus 2kq cosine phi. Yes, where phi is the angle between momenta k and q. Okay, one might look and then say, oh, it's very complicated. And like how to compute that. But turns out it's pretty easy. We can just do the partial fraction decomposition of this guy. But first we change the variable integration to x, which is k over q. It belongs in the domain from 0 to k Fermi over q. Plug that in. We will get and do the partial fraction decomposition of this guy. That leaves us with a very simple looking result. Q squared 0 to k Fermi over q dx. Dx over x from 0 to 2 pi d phi. And yeah, difference of two fractions. Squared plus 2x cosine. Yeah. Now that looks more or less familiar. There is no problem with integrating this guy, but there is a problem with integrating this guy. Turns out that you can that probably the simplest way to understand how to properly compute this integral is to go from the integration over the phi variable to the integration over the complex unit circle. I'm not gonna go through that, and as I also found out, Wolfram Mathematica also gives you the correct answer. You don't have to like spend like 30 minutes like figuring out which roots are inside the unit circle. So yeah. So the answer looks like that. 2 alpha pi u squared integral from 0 to k Fermi over q dx over x times theta of 1/2 minus x divided by 1 minus 4x squared square root minus 1 over 1 plus x to the 4th. One may say, oh, that's also a complicated integral. But the miracles don't stop there, and we can actually compute this thing exactly and get the following formula for pi over x. It's just like the matter of like carefully computing this integral and accounting for this theta function. But at the end of the day, you get an answer that's expressed in terms of the elementary function. So it's inverse hyperbolic sine of q squared over 2k Fermi squared divided by 4 pi alpha q squared for q less than 2k Fermi. And something that we don't care at q greater than 2k Fermi because the maximum momentum transfer is 2k Fermi. If we actually draw this picture, we will see that there will be like some type of cusp at 2k Fermi. I actually don't remember how it looks, but I can guess that it's something like that. It's continuous at 2k Fermi, but there's a cusp. Okay.
I think when Q is smaller than 2kF, you go like this cosine, then it goes the other way.
Probably.
Hyperbolic singularity.
Yeah. True. Yeah, something like that. Sorry, I did not plot this one. Okay, but once we actually want to do the procedure of like Kohn-Leitinger and compute these expansion coefficients into D, and also into D, we need to expand the function in terms of the cosine. So it's going to be u0 plus 2 sum L greater than 0 u L cosine L theta. So to compute those ULs, we would need to perform the following integral. Is going to be integral from 0 to 2 pi d theta over 2 pi u of theta times cosine of theta, right? Turns out that this function is analytic. This function like behaves well as a function of theta. You can actually prove that you just like substitute q equal to 2k Fermi sine theta over 2 plug that in there, it's gonna be like sine inverse hyperbolic sine of 2z over z. The only problem that it might arise from is at 0, and you can provide the explicit series to prove that it's like analytic there. So no luck.
But wait a second, but still, are there any attractive components?
Any attractive components?
Yeah.
If
you do this integral.
Yeah, if we do this integral. Okay, so
There is.
Okay.
Yeah, I actually have a figure here. So for the
Go to the podium.
Yeah, go to the podium, like.
Yeah, I can.
I mean, I computed them numerically.
Yeah, me too. So.
Okay.
So, yeah, it should be the same.
Go close to the podium. Let's find each other.
Come to the podium.
Yeah, I can.
There is a second microphone. If you
Second microphone?
Yeah.
I did. Where is that?
Yeah.
Okay. Okay, I can share.
That's it, one, yes.
Oh, nice. Awesome.
I can show you the figure that you can continue.
I think
So the figure I got, yeah. So we have a few terms here.
Sorry.
Yeah, we have a few terms here. That is for the diagram like this. Then you also have like the others. It turns out yeah, we're called BCD. And this term will give you something like the pi, which is what he showed, something like the cosine theta. But there is one that is the minus cosine theta because I mean that's simply pi minus theta. And the U of L, when you sum the three diagrams, will be something like the U0 square plus minus 1L, or maybe there is two. Yeah. And U0 U pi plus U pi square. And the thing is that we need to figure this out. It turns out for this one, without this minus 1 over L.
Interrupt you for just 1 second.
Yeah.
There are two different things here. One is possibility to get singular non-analytic contribution from 2KF. Another is just consider this as second order contribution and calculate whether there's any attractive component. So when you put this U of 0 and U of 2KF, you assume that there is some non-analyticity. And what I heard before is that there is no non-analyticity. The function is completely regular.
To be here is regular?
Right. Well, again, it's definitely non-analytic at Q larger than 2KF, but it's not what you need. You need Q smaller than 2KF.
Right. Yeah, we need to use that because we replace Q as some, yeah, like as the road here, we need smaller than, I mean, smaller or equal than 2. Yeah.
What I'm saying is very simple. There is a function. If this function is non-analytic at 2KF, when you approach 2KF from below, then you can use your expression, the ones that you put in. But this expression are obtained assuming that only non-analyticity matters. If the function is analytic, then you cannot do this part because you cannot single out only contribution coming from particular momentum. But at the same time, my question is very simple. You have this function, wonderfully have analytic expression for the function, and the function is not a constant. For K-squared dispersion, the function is just a constant, you get nothing. But for this function, you just integrate, and then I don't know what the result is.
Okay, so I computed these guys like numerically. I don't know how to, well, yeah, I haven't spent too much time trying to figure out how to compute this integral analytically. So numerically, let me look it up.
Let's sketch it.
Okay, so you're looking for a negative values of like this UFL, right? Okay, so
If your definition of U is such that
oh, no, sorry, L components of this pi of L. Yeah. Okay, so what I've got was that there are like very small values at around L equal to 10. That's L. That's pi of L. When this function, so it's like roughly 10, when it's negative. So, and then like it goes somewhat around this guy, and after that, it's kind of hard to see like right now.
Negative about 10.
Yeah, it's negative about 10.
Basically means that there is something, but also referring to what you said. In general, as we discussed in class, you need to write down all in the situation when there is no non-analyticity. You need to write down all 4 diagrams, calculate these 4 diagrams explicitly. But of course, you have a constant U, so 3 of them cancel out, and the last diagram contains pi of minus cosine theta. So then you will need to take a function of minus cosine theta, which changes sign of all odd harmonics.
Okay, I haven't done that.
Yeah. Did anyone went further than this?
So what's the final result?
I don't know. I told you from the very beginning. I'm curious.
Yeah, Vivek, I present what I got. Yeah, so what I got here for this diagram, and if we expand it as UL, we will get something like this 2 point. Okay, that's
Erase something from the whiteboard so that we will see what you're.
Erase part of it.
Okay, yeah. Is this one?
It's the middle part probably.
That's a quick question. So you mentioned U is constant because Hubbard model or what's the reason?
Well, no, this was the problem. Just if U is constant, what's going on?
I didn't see that sentence in the problem.
Yeah, I got a few points. This the average was 0, which is positive. So this is equal L and L, and we get smaller one that is positive. Then we get negative, smaller one again, and smaller, negative, and negative. I'm sorry, the positive, negative, and positive. And the other one is simply there is this I mean the other one is for the minus cosine theta. That will give you there will be some -1 right now compared to this point. Yeah, and if you draw it draw the absolute value and also in the multiplication in the multiple for the wire test.
Which one is the largest?
This one, the average plus 0 is the largest.
Which one? Which attractive term is the largest? Using the fact that you need pi of minus cosine theta.
Yeah, the largest one is okay. So for this one, I got this one is the minus, which is minus 0.2325.
But for which value of L?
L equals 1.
So P wave.
I guess so. Yeah, and you draw it in the log after the log on y, and it looks like it. Yeah, probably it's numerics, but so that shows the like the minus over L behavior for your
Which means the function is analytical.
I have.
Any exponential behave dependence with angular momentum means the function is analytical. Which it is.
Yeah, yeah.
It is.
So I guess as far as I understand, the difference between you guys is that you did not include the fact that the actual interaction, the actual renormalized interaction is a function of minus cosine theta rather than cosine theta.
Yeah, I think it might be easy to include, but yeah.
Oh, just
I know.
Harmonics. But then you agree with each other, right? Because
Yeah.
you're saying that you have repulsive harmonics up to 10, and in fact there are half of them are attractive.
Basically, yeah.
Okay, thank you very much. Yes, we have time for the last question.
You know, 10 minutes, so I guess, yes, if the first people from group one, problem three, something come up, and the problems.
There is an argument to show that for all even powers of K dispersion, there is the function analytic.
Sorry?
There is an argument for showing that the pi function is analytic for all even powers of in the dispersion.
Very, very good, but still the question is there any attraction? And apparently I hear that there is attraction and the largest is p wave, which is nice. Good enough.
Oh, no, I mean MATLAB. Yeah. That would have been
Yes, Jen, do you know how to shut off this one?
This HDMI one between.
Yeah, there's a.
One major carrier. Which one? Just says HDMI one.
Just hit HDMI one.
Yeah, is it? I think what they do is, so there's
Okay.
three, there was originally a nine.
Okay.
Pokemon.
Okay.
I try some.
Oh, yeah.
Isn't the plus at the bottom?
Oh yeah, it's just up the convention. I can take the bottom. Sure. Okay, hello again. We're back. So this will be going through the third problem. So this is just kind of doing this construction of the Hamiltonianism symmetry. So we're dealing with a space group 123, has fourfold symmetry, point group D4H, I believe. So I'll be using the same convention as Daniel and also as Bilbao. Our inversion center of this unit cell is going to be at this left corner. And then so now during the first day or I guess it was not the first day, during the first lectures, we were considering S wave. Now we're just going to be considering a P wave. So that's just going to change the character. And so we'll be considering 4 different operations. So just C4, inversion, mirror X, and mirror Z. So we're going to be considering just a 2-dimensional case. So like, so we won't be considering any like out of flame momenta. And so the first thing to do is to figure out the matrix representations of these 4 symmetry operations. So for without loss of generality, I'm taking the convention that we're working 2x2 basis, where this is in sublattice space. This bottom orbital will be just given by the first component. This one top orbital will be given by the second component. So like I'll work through a couple examples just real quick. So if we consider the representation of C4. So C4, For example, if we look at C4 acting on this, this first sublattice is going to map it to this one, so it's going to be even. So similar, if we go from the second lattice, it is going to map it to the first sublattice modulo a lattice transition. And it's going to have an overall minus sign from this place. And so, and I should mention, you can of course have different conventions in terms of the signs, and as well as as we met, this is a gauge matrix. So you can always have up to some signs, but as long as you're consistent, you'll get the right result. So UC4, it's off diagonal, which is sublattices, and I have a minus sign for one of them. So I have a -1, 1, and then or sorry, I guess on this convention should be a 1 -1. Is that right? No, sorry, no, it should be yeah, sorry, -1 to 1. Since 2 goes to -1. Perfect. So then next we have inversion. These are both p orbitals, so you can see that it's odd under inversion, but you can also do it explicitly. Except it's a diagonal, it maps to the same sublattice, so it's just going to be -1 -1. And I'll put the minus out here. I should write this down. This is just given by, I'll just say -I, so in sublattice space tau y. This is just given by minus tau naught. Otherwise, we also have the U here for consistency. The representation of a mirror X. So this is going to the mirror plane is right here. So this px orbital still maps to the same sublattice, but it's odd under this mirror X. This py orbital is invariant under this mirror X, but it still maps to itself. So this is going to be a tau z, so diagonal representation. So it's just going to be a -1 1 is equal to minus tau z. And the last one, mir z, this is two-dimensional. Both px and py are invariant under mir z, so this is going to be identity. So next, we play the game. So I'll just write down. So we have we also have identity, of course, which everything acts triply under. We just write down how these, if we consider, for example, how each of these poly matrices act under these group operations. So I'll just call it alpha. Alpha is equal again to 0, 1, 2, or 3, and UG inverse. And so I'll write down this. We're considering how tau naught, tau x, tau y, and tau z each behave under identity, under C4, under inversion, under mir x, and under mir z. Of course, there's a few other symmetries as well, but this is enough to determine what the erupts are. So first, you can go. Let me first write down what each of these operations are. So identity is identity. C4, as we say here, is minus out tau y. Inversion is also proportional to identity, but minus. So you have minus tau z here. Mir z is identity. So then let me do it. I'll write down the erupt there. So everything transfers, I'll say, is trivially under identity. And then, so then we also have these two are also identities. So I can say everything are going to transform trivially under both inversion and mir z. The ones where they can get interesting are now for the C4 and mir x. So for C4, so tau naught identity is also going to be trivial for both of them. So I'll go for C4. So tau x anti-commutes with tau y. Tau y commutes with tau y. Tau z anti-commutes with tau y. So I have a -1 here, a 1 here, a -1 here. The tau z anti-commutes with tau x, anti-commutes here, and tau z commutes with this. So if we go to our character table on Bielbauer, like the Jacobs University one, whoever one's your favorite, you have this, go to for example, the D4H character table for the point group. And so for this one, this is just your A1G representation. And then this next one here, if it's odd under C4, odd under mir x, this is your B2G, which is if you're more want to see, it's the DXY representation. And so this third one is a little bit more interesting. It's the A2G representation. I'll get into it a little bit later. And this last one is tau z, which is just your B1G, which is your dx squared minus y squared representation. And so, again, I should remind us that we're considering a Hamiltonian of the form, so I'll call it F naught of K. I'm not going to fall off, am I? Tau naught plus F of K tau. These F naught. So we want, like, we expect the Hamiltonian to be invariant under all these, all the group symmetry operations. And so, in other words, like, if there's a tau x term, then like this fx should likewise be like a function representation of the B2G rep. And so this A1G, I can simplest form to get this write down as a cosine kx plus cosine ky. And of course, it could be a constant as well. B2G dxy. So this one is going to be a sine. And so now because we actually have, we're going to say inter sublattice tunneling, but still within the unit cell. So it could be a half of the lattice vector. So this is just setting like the lattice vector, the unity. So I have say kx over 2 sine ky over 2. And so you see that this satisfies all those symmetries. A2G is actually a little bit more interesting. It's actually, there's no quadratic or cubic representations, but there is a higher order. And so you could see it is satisfied by sine kx over 2 sine ky over 2, or then cosine kx over 2 minus cosine ky over 2. And you can kind of convince yourself either by showing that, for example, like this, like B1G, A2G will give you B2G, or you can also just kind of play with these symmetry operations on your own time. And then lastly, the dx squared minus y squared is kind of the famous, like cosine kx minus cosine ky. And so we can make the one more like additional assumption for the system. I'm not sure if it, like, I think we want time reversal in the symmetry or okay. So
you should have.
so if we like impose time reversal symmetry on the system, so we're considering spinless system. So in this case, time reversal symmetry, I'll just note it as T, is there's no I sigma y because there's no spins. So it's just sublattice. So it's just going to be complex conjugation, in which case all these matrices are invariant except for tau y. So we're going to say that there's no like tau y if there's time reversal symmetry. And so the only ones that we're going to have then, I'll just write down the Hamiltonian over here. So Hamiltonian is HK. So I'll just I'll leave it as a f naught tau naught plus so fx is good. Tau x plus fz tau z. And of course, these are functions of k. I'll just add a subscript. And so then this f naught is in the A1G rep. Fx was in the B2G. And fz was in the B1G rep. And so then I think that's all for the first part. And then so now we can just we're considering now adding
That,
oh yeah.
that's great. And maybe we'll leave the second part, I think, but I'll just make
Okay.
one comment. So
Okay.
everything was great except for one thing, which turned out not to matter. And the part that's important here is this term here. So if you think carefully about the condition that you take k plus g and it clicks of a minus sign, you convince yourself that this should be cosine kx minus cosine ky, not divided by 2. So
Yeah,
like-
oh yes, yes.
Yeah, so if you were to 2 pi, I'll get a minus 1 from this, an additional minus 1 from this, and so this first term will go over plus 1.
Oh yeah, so since it's kind of like diagonal, then 1 over. So otherwise it'd be 1 with respect to symmetry. Oh, I see, I see. That's a good point. That's a good thing. And then do you want to talk about the altermagnetism?
No, how are we doing? I mean, I think
12:30, but maybe if it could be done in a few minutes. If that's
A few minutes, maybe summarize.
Yeah, I'll give the punchline. So altermagnetism, we just consider now. I'll say like some, I'll call it altermagnetism. We're considering a term where we have some coupling strength. Now we have tau z, sigma z. We're adding a spin over, like no spin over coupling, but now we're considering a spinful system. So basically what this means, if I write it down in sublattice space, is I have a sigma z minus sigma z. And so what it's going to mean is that let's like suppose that this j is negative. And so we'll have a spin up polarized to one sublattice, spin polarized to the other sublattice. If I write down this Hamiltonian, I can play the same game, take the square. Now I'm also including this tau z term. And so these are all diagonal and like identity and spin space. And then let me just write down the final thing. So what you'll find, I think this squared, I'll have f of x, I call it k squared, plus f of y squared. I'm just disregarding the A1G rep, since it'll just be an overall shift. Fy k squared, then fz of k, like sigma naught plus j sigma z squared. And so this is, you could diagonalize it exactly, but here, like, we'll basically see this will give rise to a term that looks like fzk times this coupling strength times sigma z. And so what it means is that now this ultramagnetic order, where we just have collinear spins, like that are oppositely polarized for each different sublattice, now kind of like couples to the like this now this B1G rep. And so if I were to draw out like this like spin order and kind of momentum space, say this is ky, this is kx, we'll have this nodal D wave structure. I have like spin up, compensated by spin down. And so unlike the usual anti-Fermat case where these this up and down spin sublattices are related by translation, these are now related instead by like some non-trivial a representation of the group symmetry. So in this case, it's related by some C4 symmetry. And I think that's the punchline. But if anyone has any questions, we're happy to answer. Or if you have anything to add.
So that's good. Anyone has like one or two, maybe very quick questions? We could maybe do that right now. Okay, but if not, this concludes the homework section, and I believe this is the last section of the school. So let Andrey. Yes.
Okay, thanks to everyone for coming. Thanks to everyone for surviving for 5 days. Great. I hope that you have more than just sitting in this room and enjoy the city of Minneapolis. Those who will stay here for the rest of the day, just go outside and go see Mississippi, go see whatever the city of Minneapolis offers. Those of them who will be coming back, have a good flight, beep, sail back, whatever. And see you next time. And it was really great to see all of you here. Yeah. Yeah. I Yeah, I also think so when you look at it, I was like around the scale divided by omega, right down.
This why you have L as the limit.
Project down to that same basis. I want to regularize your policy. Okay, so if you do it in financial sectors, then you're lower on it. We use that, right? I want to be able to. Wait, I actually don't have the good. Or the upper cutoff will probably be fair. There is an yeah, that's because and breaks time versus general one. Basically, you're realizing it. Oh, yeah, like TI. You still can only find a momentum, but it's over. Yeah, but so I was just saying, you can, I mean, Crystal can also use find a momentum. Last year. But it's only the same. Okay. So there I do like angular integral, etc. So that's just the bounded space. Integration is found all states. And then in the maximized, we got the expression with term blocker. But there again, you could have just thrown away because and then you say this is and then you want to express that engine for you. Well, the TI operator is like yeah, so that was so Boston D grade. It was this okay. Yes, so the TI operator was gone. And so in that case, you could have gone through the same representation, found out that there's only one channel out there. So it's just a different way of doing it. When we did it in class, we chose somehow the wrong basis. But that's because we want the superconductor to break the time reversal symmetry. So working a little bit differently than we might have expected, right?
When we have, that means we just have the one, yeah, that means we have surface.
Exactly. Yeah, so you can check that, if you work as a particle hole basis only, then you would right away get Bogdan Fermi surface.
Okay. I see. So yeah, just to understand that, yeah, there's a lot of stuff.
Yeah, so.
We only have S. Okay, so with that means we don't have.
Yeah, but how do I understand the band of that? That's right.
We have some kind of like a particle.
Yeah.
There's no
Because it's
okay, yes, so yeah, that's right.
So you can just.
Yeah, and that can obviously set the context.
Trivial polymatrix. As a.
Yeah, so yeah.
Yeah, and then there's supposed to do that, and then it's. If you make solo installation.
Like that's this.
I think that's not possible. This is still solution because you're estimating that's the my integration this. You have one and not the other. Right.
Can you
yeah.
Okay, so usually you have to do the.
Yeah.
And that doesn't expect the same. So probably like not the chapter review standard.
Yeah. So assuming you know specialization, if you have an organization.
The new terminals, right? They have to then it means that you're the fixed energy.
There is a lady thing. Basically, let's say.
Okay, that's all the risk.
Like why
Okay, so it's always that from you.
And then.
Table just with TI and CI. I thought by just looking at the numbers. Looking at the what? Looking at the TI and the I'm just.
Does it mean this?
What happens with that TI and CI?
Well,
Oh, yeah. I mean, this is. Yeah, you don't really have, need that information for that classification. So you can just go through the process of classification. You can identify something within CI, operating TI. And then you.
But you can have repeated work. So there.
Yes.
But yes, you can.
But I meant more in terms of just by looking at the table, can you tell whether that conversions obviously as well?
Yes, it's
You can tell automatically, well, this is true local conversion symmetry. You can tell that you have that sort of, by seeing that you have CI and TI suggests 16.
The question, then we're still trying to just wrap around these kinds of degeneracies. So means we have. By definition.
And then we have to play with these other symmetries. No, otherwise I'm just trying to.
There's no need to everything here is like, then I can do what I.
And if it looks basic,
the results will depend where.
Are you familiar with that case?
What you're trying to do depends on all of the things.
There's no need
Basically, I energy, I find out your particle energy. From this last piece that you were at. So you do have you do have this. Sure. Except when you know, and then you know you can. That's so non-circular form of your question, but the smallest. Yes, it's not requires you to have two basis states at least. And then you can commit yourself that physically, you know that you must be standing if you have. Yes.
But it seems to me come up in practice in theory to some degree.
Maybe then
Even the material space was splitting majors, you can only know about these houses.
Exactly, but then in the other cases, when you had a pseudospin as well, you also knew that you had to write down a pseudospin. Right.
Поэтому все появляется
That's what you get into, but in the case of today.
Не знаю, можно ли такому доверять. Смотреть, наверное, перенормировать.
This argument, and then that makes sense to you. I think it is more strong argument for actually in that case you
should have a whole basis as well in your Hamilton.
Yeah, in order to add this.
Something to.
If you. Okay.
That's what.
But I mean, it's good.
You guys think.
So then you. Поздней весной.
This was good. I know, otherwise it's. Yeah, exactly.
Вымазано в
Right,
Yeah, I
right.
can choose the H to be on the direction.
Exactly. And now you got all the material ready right now.
And I will get.
Oh,
Yeah, so you're, so it is weird that in the single band case, and when we have pseudospin degeneracy, we have an SU2 invariant. And so then you're saying, what did I do?
So so I guess the argument, so.
But what we do
Now
is secretly spin orbit as a
Stuff like this.
So we say we need to have some representation of particularly when we put spin triplet. Buried in that way, the basic spin orbit. And so you say sigma x, sigma z.
Right. So you see, so this is a downstream question, this is next step to do.
So you're right.
But in that case, you need some input.
And then you can ask,
Say,
what happens if
specific.
actually then allow for.
That's like a single long thing.
So
You need those.
subtle because strictly what you two band system.
This one.
Three band system.
That's it, because when you.
They go to the eigenbasis, single band, and that's how it's fit on.
Делать
Where we just put in like.
There also is a stupid, you know.
потом поеду, мне самолет
I mean, like actual.
Or you think maybe sometimes.
Second, you have.
Maybe it's complicated where you only continue the part of it because where you can.
But the single band system, that's been our allowed because of the pseudospin degeneration, you must have a diagnosis. But then you single band with spin, but then you have pseudospin degeneracy. So I mean, a single band with pseudospin degeneracy.
Sigma zero.
Yeah, so you have a sigma zero Hamiltonian, so there is, you know, no sign for the spin. Okay, and so. Somewhere. And then.
You know that.
Is there any?
So that's like
Something.
it's the one I write down something.
That's the Y, so
See what's the pairing. But then it seems like this method would not take into account.
That's where the spin.
Well,
It's way away from.
And then there was no such thing, I should in principle.
oh, okay, because I thought when we spent around, say, around point, you know, go back.
How long the components, things like that, so there's a lot of.
You have less.
Yeah.
If that,
Is that freedom and the triplet, the momentum increase in freedom, and then they're on the opposite first approximation.
I think you can capture.
so sorry, say that again.
Let's see, so there's, yeah, so you have. Yes,
Because any stat.
So you have P vectors reveal, and then that's the K dot sigma, and that's the.
Purely.
Right.
It depends on language.
And just like.
So in this case, you get the same understand
One.
where that pocket is will seem like gamma and zone corner.
Yes.
In that case,
But analogy was.
still right now. What they think. Alright, what's the most reasonable way of doing that? It's the order.
No, I don't think so. I mean, honestly, I did use one nanos. I mean, I took P one of those, and then I just used the average. So there is no, I didn't. And then even that very last part of part one, that form is never. So you
the magnetic field.
the magnetic field together. I was surprised to see that.
Oh, yeah, no, let me know, whatever, yeah.
I have.
They use it today.
Oh,
Okay.
So I'm agree for something there.
Oh, nice. Traffic not too bad. Usually,
Well, that's because it's.
이날이란 so what's missing was Anderson, that is the new thing.
Yeah, but when you say.
And
Yeah, so here is this. We had, so. Now the system I showed you just motivated more than like.
don't get it in one direction, on the other, so in that case, what we only consider just type of reserve, which has a broken sequence. Do you think that usually?
And it will.
Yeah.
Складывать, нажать на лист.
Right, consider this type of benefits. People just want battery. It seems like it would have.
It's exactly what happens.
Exactly change the. Yeah, no, yeah.
More things than one wrong. Yes. One is moving and one is ready. Yeah.
We still have a bit of time. Yeah, so, I mean, yeah, so I mean,
No.
Yeah, and I will tomorrow. It stays the break. Yeah, actually, yeah. Because the flag was never part of.
То есть, например, у полиномов не так-то много.
Exactly.
How do you even start?
Yeah, maybe, I feel like it's more an optic side. More years. I mean, so, like, so, for the experiment we worked on, I knew in the end, like, a single band. So everything they were seeing, so they were seeing the surfaces, they were also seeing the straight distortion, which suggested that they were getting magnetic equation. And so we knew the single band had to be right, so then we just started playing with that, doing what you guys are doing in exercise one. So how can we get these fundamentals, what can you do it, and the first solution is wrong. So the first solution was really, that's physics coming, but that just didn't feel right. That's a finite video field. Didn't look like it was really happening. You're saying you had to. So then we realized that there was this extra term that could be added to Hamilton. But it was really. The epsilon minus also. So once we understood that, then we could get. You need to understand that your first guess. You can know that some limit is right. You know that you wouldn't be able to have. Like with altermagnets, very early days, everyone was doing basically a Hamiltonian that was single band, and they added a sigma d times some.
I think
And that's the easiest way to describe it, but it's clear that that wasn't right, because what everybody was talking about.
have negative component.
But did you include this -1 to power of L?
So we said, okay, let's just
This is
try to
one.
add a
Okay,
sublattice and see what happens.
how does?
So then we realized.
No,
Because it's like standard theory, right?
Yeah.
Come out.
So this cancel out this.
In the matrix.
It's still constant U. And then the only one you have is
Calculate where that comes from.
whatever it's this is K plus.
So it was nice to see that.
And for all what components have a different sign.
Parameter as a consequence of the end.
Напи.
But then if you explain that more, you can get all this.
And therefore, if you have for L equal to 1, if you have attraction, so if you have repulsion, then you have to replace it by attraction.
Yeah.
So what you get for L equal to one?
It just.
Okay, I haven't.
It does.
Okay, so far it's like.
Most cases, it is.
Negative, but then you have to change sign because of.
So thermodynamic.
So, yeah.
It becomes negative. Negative means that.
Get some interest.
So you
in
get P wave.
signatures and
Yeah.
Nice, it's what you
finite
expect.
frequency
Nice.
conductivity, so you
Nice.
get. Yeah,
Yeah.
but.
Good, I didn't know about.
So.
Very good.
So you
Yeah,
can
and I
examine
found,
all
like,
this, but basically.
Two plus one.
Yeah.
The integral.
Yeah.
You there?
Ugly, but you do it numeric.
It's still.
Yeah.
Numerically, yeah, I think.
Yeah, really, I mean, it was interesting, that's like.
I think
That was a
yeah,
very.
I think
anomaly that we could
Yeah.
actually- We wondered, Eric's.
Integer plus.
I somehow managed to convince myself it's
And
going
then
to be a little
serious.
rush.
That wasn't an easy thing to figure out, but once we got it, it was clear.
But in some
That was
sense.
it. But there were already
at least
hints
for
in the
model,
literature
it
that
doesn't matter.
things like this happen, so,
Yeah.
you know, we knew there was a so-called
Because at the
repairing
end of the
state,
day, we're
and
talking
Wilczek
about-
had a lot of similarity to what we were seeing, so
So
it's gotta be
Main question
something along these lines.
whether case where.
We understood, we're
Constant-
kind of were, but not
constant,
exactly.
polarization bubble, it doesn't give you
And
any
also for this
component
course, you
effect,
can't really define.
whether this is specific for case, or there is something.
No, you can, you
You're saying no.
can, in the simple case where you put a
Yeah.
Zeeman field or.
Okay, guys.
Or even if you put this epsilon minus term and you add that to a E-wave superconductor, you can easily calculate the charge of each particle on the Fermi surface. And you can easily show that the charge over the Fermi surface is integrated to zero. But that means that, you know, you have arbitrary linear combinations, except for maybe this point where the Boglio Fermi surface intersects the original Fermi surface. Those were equal admixture particle, but as you moved away from that, it became, you know, one side becomes a particle like the other side is more. And so
Like,
you
what's
have
your
no,
function?
there's no charge, and that
Because like
kills
this,
your
this function is
quantum
like,
oscillations, actually.
it's like
Quantum
fully
oscillations need
irregular
the
in
same
zero.
sign charge
You
to
can
go
even
around.
like write like this.
And so if you have a charge that's changing sign, all that would happen is the electron would come and maybe bounce back or something, but you wouldn't get an orbit. So you never impose flux.
And the zero charge, symmetry or?
The zero charge on the, where you intersect the ratio, it is guaranteed by symmetry, because that's where the, that's where the.
No, it's not like forcing, it's
Yeah,
just like, it's just, you know, this function is already. complicated.
Oh, no, but I guess.
So,
The original.
Yeah, I think that's right. I think that's right. Yeah. Yeah, I think that, I have to go back and think about detail, because you know the epsilon zero term. But the epsilon zero term doesn't change the linear combinations of the eigenstates, right? It's just a diagonal term you're bugging with the Shan Hamiltonian. So the original Fermi surface must be exact equal combinations of particles.
I think you.
Okay.
So it's a lot
Yeah,
to
no,
digest, but thank you so much for the pictures. Great school.
Okay, I'm glad you guys enjoyed it.
Yeah,
It was great to meet you guys.
Thank you, you took this somewhat complicated.
Much appreciated. Purpose, right?
Are you flying back?
I know my wife is here, and so I am here for the weekend.
Okay, so
Yeah.
the thing is that
May as well make a
it
little
might
bit out of
be,
it, so.
that's for
So you
two
have
smaller.
Sorry. Oh, that's not
Yeah,
yours. Okay.
No, that's not.
Okay.
I'm a tennis player. though.
And we were and it was might be related with our.
But there is like this.
Pleasure working with you.
Pleasure.
Okay, so our.
I'll see you around.
Where's there a
Flying out
member?
today too?
Yeah, I'm flying out to
Like-
like 3:30, so
Oh, I guess.
I gotta get going pretty soon. I'm still flying, but. Yeah. Actually, can you give me your number, just, you
Oh,
know,
yeah, we should definitely like catch up.
you know, if you find yourself in New York, traveling up from Baltimore, just let me know.
Well, like I same as well, if you're in Baltimore area.
Sure.
Right.
So, what you're saying is that, what's your name?
Well, fine. Next week.
Yeah.
Okay, because like Wolfram is
Yeah,
actually
actually,
like
that's
relatively dumb, especially if it comes to computing.
Nombre
Like
capelitos.
this integral.
So we keep it up.
So it might have spit out.
Are you
something
Spanish already?
here.
Oh, no.
Or like Latin America?
I'm actually Italian, but.
Ah, okay. Why are you integrating these? Okay, thank you.
Thank you.
Present price. Okay. Sweet, man. It's been real.
That was fun.
I'm sure I'll see you around the future, or at least at March meeting. Yeah. Yeah, I gotta go get food and then.
Oh, is it free? Is it like?
There's a lunch.
It's not that version issue. It looks like it's, yeah, look. Yeah, so when you take this integral over k, it might seem that it diverges, but if you actually like compute the phi integral first, you get like 1 over x, like where x is like the integration area. But look at these guys. At near x equal to 0, you can expand these guys, and the leading term would be x squared, which cancels out the divergence.
That's x squared and okay.
Okay, and so but why did you extend the integral to infinity? Because yeah, you have like the limit here from.
Yeah, and the minus.
Ah, wait. This term is not present. It's theta kf minus p.
Yeah, I understand that because I changed the and here for both the thetas, and their relation is simply like theta minus x equals 1 minus theta of x. Yeah, so you will have from 1
But like originally there are like Fermi distributions there, and at 0 temperature they are 0 outside of there is 0 for k greater than k. You agree?
Yeah.
So you have 0
I mean,
outside of.
not exactly because here in order to have 0, you need them to be
Okay, so I don't. Yes, I think that this is the correct expression, but this corresponds not to this guy, but to kf minus p.
I understand, but the minus epsilon p theta minus epsilon p will be 1 minus theta epsilon p.
Yeah, great.
So I changed that. There is a common factor 1 from both, and they were cancelled. Then I got this one.
But minus p1 minus theta of p, but for p greater than pf, it is 0. But you don't get a 0.
I don't.
So
For this
I see
function,
an
yes.
inconsistency.
But in order to have a non-zero for the denominator, that is when like one of them is inside the Fermi surface, the other is
But this guy is 0. At 0 temperature, this guy is 0. And then like that's like because.
One momentum can be inside the KF, the other can be outside.
But at 0 temperature, you don't have momentums outside of KF. You can be outside of KF, but like wait, P can be outside of KF.
Yeah, that's what.
No, sorry. No. P cannot be outside KF. Because like you have this guy because
I mean, the reason why the reason you claim cannot be outside of the Fermi surface is because we have this theta function, right? I changed this theta function to like this.
Okay, well, let's like examine this guy's closer. So it's like it's. So it's what? Theta of like mu minus epsilon p minus theta of mu minus p plus q, right?
Yeah.
So what you're saying is that, this is just.
Yeah, if I change the argument, there is a 1 minus out of p.
But. Yeah, you cannot you cannot do that because like you should leave it like inside the Fermi, like and you like integrating outside of the Fermi where there is nothing.
Yeah, I understand that. That argument is when you keep doing this and change variables, then you get a theta that need your p to be inside of this. But I can change the argument to minus mu plus epsilon p. That is simply the like the property of your theta function. I didn't do anything. It's like I'm